Ladies and gentlemen, first and foremost, I extend a warm welcome to each one of you at the İZPHOTECH event, hosted by İzmir Institute of Technology with contributions from Optica, IEEE Photonics Society, and the İZTECH-OPS and Photonics Society. My name is Viviana, and I'm a second-year student at the Photonics department. It's a great pleasure to be among you for the next 2 days during this significant event. Through this event, we also take pride and joy in celebrating the 100th anniversary of our republic. Now, I would like to turn the virtual stage over to Professor Jain, our department chair and advisor, who has played a significant role in making this event possible. I invite her to deliver the opening speech.
So good morning, everyone. My respectful and dear Head of Scientific and Technological Research Council of Turkey, TÜBİTAK, Professor Dr. Hasan Mandal, my Rector, Professor Dr. Yusuf Baran, dear colleagues, and our precious students. We, the İZTECH-Photonics family, are honored for organizing the talks on Photonics Science and Technologies at İZTECH for the second time this year. We, the İZTECH Department of Photonics, İZTECH Optics and Photonics, and IEEE Photonics student chapters are organizing İZPHOTECH to celebrate the World Day of Photonics. With the contributions of IEEE Photonics Society Turkey chapter and Optica, formerly known as the OSA. I would like to thank our students for their dedication and hard work, and the mentioned international organizations for their financial support. As the citizens of the world, we all are living in nanotechnology evolution, the century of photon-related technologies, and this year, 2023, as the ones living in Turkey, we are full of joy and pride, and we express our gratitude, responsibility, and excitement for the 100th anniversary of our country's foundation. By using this opportunity, I would also like to remind another event named Achievements of Our Republic in the 100th anniversary of its foundation to be organized in İZTECH next week on November the 1st. As a woman living on these lands, Turkey, I'm grateful to our Republic for providing me the opportunity to present my skills, talents, capabilities that make me happy, and the skill sets that I use in my private life available for a wider population. Our next generation, students, as a faculty member, as an advisor, as a board member, head of department, etc. To our future generations, regardless of gender. I'm grateful to everyone who funded the Republic and ensured that the gender equality laws that exist in our cultural life were passed on in written rules, regulations, and laws, but most of all to Mustafa Kemal Atatürk, our great ancestor and the founder of Turkish Republic, who took the initiative and encouraged those around him to take the initial steps. I also would like to thank our rector, Yusuf Baran, for his sincere efforts on our future and our students. He always makes time in his schedule whenever the students of İZTECH ask for it. And also to our head of TÜBİTAK, Professor Dr. Hasan Mandal, who agreed on last-minute changes, registered to our meeting, officially registered to our meeting, and attended the opening ceremony of our Day of Photonics celebrations. His presence gives us, the Photonics family of İZTECH, great support. Throughout the İZPHOTECH 23, we will have the opportunity to listen to over and overview 12 talks on valuable contributions to photonic science and technology, mainly on the topics of lasers and fibers and display technologies. 7 of those presentations will be in person. I would like to thank all our speakers for dedicating their most valuable assets, their valuable time to us. Our celebration of Day of Photonics İZPHOTECH 23 has taken 289 registrations all around Turkey, Almost 100 of the online attendees are from departments of photonics at Gazi University, our sibling department. I send my heartfelt sympathy to Gazi Photonics. I welcome all our in-person and online participants and hope that these valuable speeches, which most of them will be streamed and archived in the official YouTube channel of İZTECH Optics and Photonics student chapter, will contribute to many photonics enthusiasts. Let's appreciate the importance of photonics in our life. Thank you.
Before we move forward, I extend my sincere thanks to Professor Anvar for gracing us with her presence and for her instrumental role in bringing this event to life. Her dedication and leadership have truly set the tone for what promises to be an enlightening and inspiring occasion. Now, it's my honor to welcome to the stage our esteemed rector, Yusuf Bara. His unwavering support for academic endeavors and commitment for fostering an environment of innovation and knowledge sharing have been pivotal. I invite Rector Yusuf Baran to address our distinguished audience and officially inaugurate the İZPHOTECH event. Thank you.
Honorable President of the Technological and Research Council of Turkey, distinguished scientists, dear invited speakers, and ladies and gentlemen, and my dear students, it's a real pleasure for us to host this event in our university. And more importantly, it's a real honor and pleasure for us to have the president of TÜBİTAK in the opening session of this international event. It's a real pleasure for İZTECH to have Master of Science for Photonics in 2017, and then PhD program in 2018, and then Bachelor of Science degree in 2019, and then have the first alumni of Photonics department in 2023, the celebration of 100 years of Republic of Turkey. So as a leading institute, we develop the future and today's leader on photonics discipline. So we give the Bachelor of Science, Master, and the PhD programs in our university and running a lot of advanced research in our university and develop the human resources in this field. And we are on the edge of 100th anniversary of Republic of Turkey. And today is a special day for Photonics Department, Photonic Day. So through this celebration, we organized this event together with our one of the most active actually student clubs, which is Photonic Student Club. And I know it very well. Even during the pandemic, you organized a lot of events, person to person or virtual meetings, and you never stop your activities in any difficulties. So I don't want to extend my talk because I want to give the floor to our president. So I would love to thanks and congratulate all the students and the professors organizing this event. And of course, all the invited speakers, all the participants to make this event more and more fruitful. So thanks for coming and joining us. Thank you.
It's with great honor that I invite to the stage Mr. Hasan Mandal, the president of TÜBİTAK, whom we are privileged to have with us for the opening remarks. Please join me in welcoming him.
Yusuf Baran Hoca, dear invited guests and the Department for Photonics, so dear colleagues, students, ladies and gentlemen. So it's a great pleasure for me to be in here. I mean, today I have a series of meetings already planned in advance. But this is as our head of department has already been mentioned that it's at last minute. I have been asked by the rector that while I am in here, so there's as an event on Photonics Day. So I said yes. Then I just make a very short preparation, at least. With also considering the attendance of our international colleagues, so to say a few things on what we are doing in Turkey. So I'll not as a long talk. Just very short, but I'll do my best. So I just trying to say also the in terms of the topic. Okay, you are the experts, but in what I am trying to say in here, how we are trying to change the ecosystem, and not on specifically on photonics, but in general. And we are just coming for another meeting at IZTECH on quantum technologies. We discuss about that how we can work together and co-create together. Yes, so yes, scientist, but I am not in the field. I am more on structural side, so more high pressure and high temperature materials. But so I just try to make an homework. So on and I have been just learned, maybe unfortunately, sorry. So the October 21st is the Photonics Days, and it was set on started from 1983. Yes, it's correct. But it's 25th year. Yeah, it's not 30th year. 30th. But as a day, I think it's a celebration. Yes. Is on. In somehow I don't know. I try to understand, but I couldn't find it. Why it is not 30th Photonics Day instead? This year is set in 25th. Times has been anyway, but I think I think it's an important because we are as already been mentioned. We are moving from electronics to the more photonics. So there is more optics type of solutions are needed because of many reasons, and including either from climate change or from the type of new instruments or the type of applications. But when we are checking the type of an area, so it's covering the communications, energy, security, transport, manufacturing, health, and agriculture. So it's covering every extent. So which means that there is a bright future. So, but maybe still not enough awareness. But I think there will be more and more in future. And so this is the first department in our country. Started from the master, PhD, and our rector already been mentioned also is also in bachelor, and the first graduates came out this year. Okay, yes, yeah, correct. And also checking from in terms of especially the frontiers type of an areas, and so this is from the year 2022. In every field of the physics, the type of what are the focus areas. So every year has been published, and this is on perovskite, light emitting diodes. So this is an area. Also, we have been putting a lot of efforts on basic science, but also in terms of the implementation, especially from the perovskite system for the solar panels as well. So we are putting a lot of. There is a. Maybe you will hear soon that there's a big investor coming in here, and also a colleague from the EPFL. They are making a joint funding together in a kind of an opening a big company in southern part of the Turkey in Adana. Yeah, you can see in here. But our aim is how we can improve the impact in here. So, and this is my more comfortable area. So this is I know the topic why is important, but how we can make it more impact. So this is the ecosystem, how it is changing in globally. So which means that if you want to make a more impact, so the knowledge creator and knowledge users or technology providers and technology users, they should work not only together, they should co-create together. So which means a type of a reversible type of interaction between them. So the role of the knowledge creator and the role of the knowledge user, not only in one direction, should be a reversible. So therefore, a kind of potential is so open science and open innovation. And also, when we check the type of an areas, I think the awareness, not only in terms of the science community, basic science, natural science, and engineering science and health science community, but also we need the awareness in social science and humanities, because this is, I think, make the whatever the area, especially like an area on photonics, still in early stage, at least in our country, for need to be more awareness in the society. So what are the societal impact in addition to the impact on technology and science, basic science in oriented. So there's a more social science and humanities type of impact also needed. So therefore, in our ecosystem, what we have been trying to do, co-create together. So TÜBİTAK, has been already mentioned, is the main funding agency of our country. It's founded, has been mentioned also our head of department and rector, that we are celebrating end of this week, on Sunday, 29th of October is the 100 years anniversary of our republic, and we have been also celebrated the 60th year, of TÜBİTAK. We have been founded in 1963. And we have been, as I said, the main funding agency for all ecosystem, for the universities, for the industry, for the individuals, entrepreneurs, and also increasing the awareness in science and technology in all levels, and also responsible for international cooperation for the science, technology, and innovation. And also at the meantime, we have been doing on strategical areas or by means of our research centers. And in that respect, there is not a big group, but there is a group also working on photonics in our TÜBİTAK research center. So total number of our researchers in all disciplines is 5,000 researchers, full-time researchers, and very small groups also working on the photonics. And this is our priorities on the left-hand side. So of course, the climate is one of our issues. So when I checked on also what type of potentials on the photonics, it of course is relevant to the climate, and this is giving a big earmark. And also at the meantime, the human-centered technology development, Industry 5.0. So digitalization, it's also making. Maybe when we checked our priorities, maybe not directly you can see the photonics, but yes, there is a kind of a cross-cutting area in all these priorities, and this is showing what we have been concentrated and why we have been concentrated. So the economically, social, and the national security, and also we are trying to be. You can see in here that how we can try to achieve, so by means of the new knowledge creation models and also the new human capacity models. I'll give an example. So these are our priorities regarding to photonics. So under the two headings, so this is on working on the priorities including new photonic devices based on the silicon-based photonic technologies, nanophotonic sensors, plasmonics, and optical communication and materials. So these are, you can see, we have been putting our efforts from the technology readiness level between 1 and 6. So you can see some subtopics. These are our priorities for the year 2022 and to year 2023. And this is another one on the lasers and the components of optoelectronic devices, lighting technologies, fiber optic technologies, new photonic measurement technologies, optical metrology, and quantum optics. Also, again, has been named in here. So again, 1 to 6. So still in early stage. So which means that I'm still are putting most of the time our efforts in many disciplines or many technologies, also including to 7, 8, and 9. But in photonics, still we are in the early. So there is enough room and enough potential to collaborate and co-create together. And so this is how we are trying to achieve. So these are different type of funding programs by our council. And so especially what we have been trying to do, we are putting our many efforts on of course, trying to increase our potential by individual projects, but at the meantime also we are putting more big numbers in terms of the budgets to funding the platforms rather than the individual project. Of course, we are funding individual projects, but we are putting also, so in here, so as an example, in here, so I mean, there are 20 platforms are running in different areas, and one of the platforms has been funded in here. So you can see in here, so the quantum lasers, devices and applications, and is coordinated by the IZTECH, but also collaborating with some other universities I mean, have a capacity in this, and also bringing the industry as well. So there are 4 industrial partners and the 4 universities come together, and their work, I mean, it's a kind of a, I mean, there are philosophy in here. So under the normal circumstances, when we fund the project, so we have been control everything from our headquarters. So which means that I mean but in the case of the platforms, so we transferred our role of TÜBİTAK to the respective platform, and the platform coordinate on the behalf of us. So which means that they are funding the projects. So they are, I mean, selecting which stakeholders, which universities, which companies. So, and we have been, as TÜBİTAK, we check in certain period of time, a year period, or 18 months or 24 months, what is the progress in terms of the impact. So this is our, I mean, our role as TÜBİTAK, but we give our role in terms of TÜBİTAK. I mean, which projects and which type of funding is going. Of course, there is a budget is given to these platforms, but they have been distributing to the individual projects, and they also invite the which university and which company to get the right bits. And these are dynamic, so I mean, they can start a project a year after, or they can invite another partner while the project is running. And also, it is during these platforms, the international partners and the universities, they can also join to these platforms. And of course, they are quite relevant, the quantum lasers, but of course, a photonic platform also can be, I mean, if there is enough stakeholders come together and with the right technology roadmap, and this is which we are very sensitive, so if they are coming with the right technology roadmap, so we can also be considered that is going to be funded or not. And in terms of the international side, that I mean, as Turkey, as TÜBİTAK, we have been collaborating with 68 countries, so with these all green areas, and with the more than 100 institutions like equivalent to the TÜBİTAK. So these are the giving a kind of a joint funding or collaborative efforts in a level of the from country to country, or more than multinational. And of course, there is I mean, I can see a big potential, because starting from, I mean, every year normally the UN has been dedicated a year of something, but the period for 10 years is dedicated and is announced this last August for the international decade for the sciences for the sustainable development. So by using this opportunity, I mean, there is a potential for make the photonic science and technology area more remarkable, and giving a potential that how it can be a right type of area in terms of a cross-cutting area for looking for the solutions for the especially for the climate change and sustainability. And during this conference, I have been tried, and when I have been also checked that, I mean, what is the priority for this year for the Photonics Day is more the, I mean, for the development of the young talents. So I am very pleased that, I mean, who is organizing this event, so it's not only by university academic staff, also including the university respective clubs or the societies or organizations are the partner of this event. So I congratulations also to our students who have been contributing to this event. And I am checking that, I mean, it's covering the all aspects. So this is also, and it's also, I mean, it's covering many experts coming from around the globe, from the different kind of, institutions, of course, from our country, but also from the different type of continents. So I am sure that it will come out with today and tomorrow will be fruitful discussions, and we are looking forward to some kind of the outcome and kind of the remarks from this event by means of our rector and our head of departments. So by this way, so once more, so I congratulate your Photonics days and looking forward to. Unfortunately, we will move for another meeting, so I could not able to join. But my, colleague, Dr. Orkun Hasakioğlu, he's giving an advice to me on this area. Quantum and especially photonics. So he will stay here. So he will take the kind of a notes, and I'll make the follow-up process. So once more, thank you very much, and fruitful discussions.
Thank you. Now we have a little break for 5 minutes. Welcome again. Thank you for your participation. Wish you an enjoyable knowledge-filled experience through the event. It's my sincere honor to present Professor Anvar Zakhidov, Deputy Director of UTD Nanotech Institute, at the same time founder of the Quantum Research Center at Samarkand University. With more than 400 published papers and H-index of higher than 70. Professor Zakhidov has 25 USA patents in the field of advanced materials, including conducting polymers, carbon nanotubes, perovskite, organic PV and LED, and various other materials and substances. Furthermore, he theoretically predicted and co-pioneered the fast photo-induced charge transfer from conjugated polymers to fullerene molecule C60. He acted as supervisor to many professors of our day and made great contributions to Photonics Society and Technology. We felt very lucky and special for hosting him in person during our Day of Photonics celebration. Please join me in welcoming Professor Anvar Zakhidov to share his profound insights.
Good morning, dear friends. Assalamu alaikum. I am coming from Uzbekistan, and Turks call it Atayurt. And today I represent University of Texas at Dallas, UTD, and the Nanotech Institute. I will explain about it. But most importantly, I am back to Samarkand. Samarkand is the ancient capital of Uzbekistan, of Turan, 2,500 years old. And we have created a Quantum Samarkand Center, to which I invite all of you. So let's start. And today I want to dedicate my talk to Nobel laureate, the only Nobel laureate of the Turkic world, Professor Aziz Sancar, my good friend. And recently Aziz Sancar visited with Hasan Mandal, Samarkand 4 times. And there is special laboratory dedicated to Aziz Sancar in Samarkand city. And there is Uzbekistan Aziz Sancar Burs. 8 students, maybe including you, can do exchange research, but 8 students from Uzbekistan should come here. And my role is to send someone to your Izmir Photonics Center. I will speak today about perovskites, which were mentioned in the introduction of Hasan Mandal. As you remember, he mentioned that perovskites are now used in very bright light-emitting devices. And there will be very special collaboration between EPFL and Turkey to do some development at industrial scale. So I will today speak about very fine detail of very new type of light-emitting devices, which are called light-emitting electrochemical cell. But before I do that, let me keep introducing and making dedications. So I want to use my talk to tribute to Alan McDermid, who was absolutely great New Zealander, got his Nobel Prize for conducting polymers. And conducting polymers are part of organic light-emitting devices, organic solar cells, on which Professor Jain worked and Serdar Sarıçıfti worked. There is another Nobel laureate from Texas. His name is Richard Smalley. He got his Nobel Prize for Fullerene molecule, C60, on which I spent so much time in my life. And he created actually carbon nanotubes. So these two great Texans, they established a lot of good centers in Texas. And Alan McDermid used to say, science is people. And we have our nanotube Nanotech Institute of his name. It is called Alan McDermid Nanotech Institute. And these are two teams where we created carbon nanotubes and new nanophotonic devices. And if you want to contact me, here is my email. I represent physics of nanomaterials. We work on different types of carbon nanotubes, photonic crystals, perovskites, and I'm actually the deputy director of this institute. So I want to thank my collaborators from United States, particularly my students. And important one there is Masood Allah Bakshi. He comes from Iran. And there is another student, Aditya Mishra, from India. We are very international. We are missing Turkish students. I want you to come. And I'm proud and happy that yesterday 2 students, one is here, stand up. She is wearing our t-shirt, UTD. And I want you to become members of UTD, University of Texas at Dallas. And also, several years ago, I created the beautiful lab, which is called Perovskite Lab, in St. Petersburg. And that is behind, you see 4 chambers, all connected, M. Brown. We created many nice devices. So some of the work which I will discuss today was done by those students in collaboration when they visited my lab in Texas and when I visited them during all these years. And now it is Samarkand National University. This is the symbol of it. And we have Samarkand Quantum Center, which I want you to welcome there. And at the end of my talk, I will show the structure of that center. Anyway, this is now the beginning of my talk. I want to speak about ions and perovskites, ionic migration, and the role of it in so-called single-layer perovskite light-emitting devices, which is very different than multi-layer. They are better than multi-layer existing perovskite devices. They are more stable, brighter, because we add additional components. We are adding lithium salt and we are adding special polymer. Sorry, I am keep pushing the wrong thing with my big finger. The polyelectrolyte polymer, which increases the lifetime better efficiency, and I will explain you why. You are all new students of Photonics Center. Everything depends on the details. Then I will show that if we add the ions as a guest to host perovskite matrix, then there are very beautiful effects happening. We can change the color either by concentration or just changing the voltage. Finally, everyone wants to have a blue device. Blue device was always the dream for the bright blue device, and we were able to create bright blue devices by making quantum dots and two-dimensional quantized layers of perovskites. So this is the talk, and if I have time, I will speak about so-called memristors, where people can use the memristors for neuromorphic computing. Anyway, So this metal halide perovskite, as Hassan Mandal mentioned, is very important new material of these days. Because of this material, which has very narrow, very beautiful colors, photons are coming there with high intensity and very narrow pure color. And we can change the color just changing the composition. And this type of material is used in all sorts of photonic devices. Solar cell photo detectors, LEDs, lasers, radiation detectors, and the efficiency of those was keep growing as compared to quantum dot and as compared to organic. They were all becoming better and better. You see here, this is organic LED. You know that if you have Samsung telephone, it has organic LED. If you will buy the best TV of Samsung, it is called QD LED, quantum dot LED. But perovskite keeps very fast growing and increasing the efficiency, and the line is most narrow here. And we are doing it better and better. But it has problems. The problem is related with instability. And instability, by the way, this is the highest efficiency solar cell, but probably you know about this. Today I will speak about LED. So, what is perovskite? Perovskite was found in the Ural Mountains last century by the Russian scientist and actually German mineralogist, but called perovskite because of the Russian Graf Perovsky. Classical perovskite is titanium, calcium, oxygen 3. It has nothing to do with my talk today. It is classical stone which is not used in photonics. Our perovskite is ABX3, where X is not oxygen, it is iodine or chlorine or bromine, halogens. All these halogens make a magic. Because of them, for example, in this, methyl ammonium, lead, iodide 3. It can be bromide 3, it can be mixed, it can be chlorine with bromine, and we see all the colors are changing. But this beautiful material, you know what is gallium arsenide? It is best semiconductor. Gallium phosphides, gallium arsenide, they are used in all these LEDs. So this material is like gallium phosphide. However, it is very easy to make it. It is like kitchen salt. White powder, you mix it with the solution, 2 different white powders, precursors, and you can make a thin film. And it works better than gallium arsenide because it has better mobility, it has better lifetime of carriers, it has long diffusion length, it is high absorption coefficient, high emission, you can bend gap tunability, and it is defect tolerant. If you make it dirty, electrons do not feel it. So there is some intrinsic mechanism that tolerates the trapping of charges, which is magic. And theorists are trying to understand it. So this is very interesting material. And all that has, of course, you cannot have only advantage. There is disadvantage. Like kitchen salt, if you will drop a water on it, it will dissolve. This material, if it is on your roof or in the device, it can easily dissolve, and you will lose it. So it is sensitive to air, to humidity, to oxygen. It is not stable. It is not stable to electrodes. Any device needs the electrode. Electrodes corrode because of iodine, cesium, and bromine, all these materials which are components. They are in ionic crystal. This material is ionic crystal. All the semiconductors, silicon, gallium phosphide, gallium arsenide, they are called covalently conjugated materials. They are not ionic. This is ionic, like kitchen salt, because this is cesium plus, lead plus, iodine minus. It means that ionic species here, look, ionic species, they can move all types of movements. There are vacancies. If there is electrical fields, because ions are charged, they start moving and they destroy the lattice. They create hysteresis in the world. So all that was supposed to be bad, and people were trying to avoid. So what we did, we thought, oh, maybe we can use it for something useful. But for that, instead of intrinsic ionic species that are parts of our lattice, we put extrinsic ionic species. We add additional ions which are small, mobile, or functional, and we use them as sacrificial ions. They do some job, but they do not destroy the lattice. Of course, there is no space there inside for additional ions, even if they are small. That's why we add somewhere at the interfaces the polymer, and the ions, additional ions, can move in that interface. We actually do not know exactly where they move. We just see good stuff happening. And I will be speaking about that. Or we can also add external ions as ionic salt. There are so-called ionic salts. We can put them on the top and then apply voltage. Ions will go inside, outside, and will do something useful. And I did it with students on photovoltaic cells, but this part I have no time to discuss today. So, there are three messages today. Ions, which are generally viewed as a problem for reproducibility, hysteresis behavior, stability, they can be actually a good player in this polyperovskite LSE game. Small ions, they are mobile, they improve stability, and they create PIN junction, intrinsic PIN junction. External ions can be functional. They can emit light. They can be something which is useful not only in movement, but in light emission. So, and also we can use them together with quantum dots, right? Now, quantum technologies are so important. So there are many, many applications of perovskites, as already told, not only in photonics, they are used for biology, other stuff. So what we did, we added the useful ions and we changed the architecture of the device. And by this, we can improve the devices because all this bad stuff from ion migration, we are harnessing it for good, as I will explain you in the next few slides. So this is the picture of the cover article which we had. You see, it has only three layers. One layer is the electrode, one layer is the bottom electrode, which is transparent on the glass, and then there is this layer of perovskite. But it has inside some additional stuff. And there are many papers. If you're interested, these are recent papers which we published with, you see, this is Masoud Allah-Bakhshi, this is Mishra, these are Russian friends. All these are single-layer devices which show the beautiful blue color, stability, and other things. So let me remind you how the usual OLED, which is in your Samsung, works. It has many layers. You see, it has so-called emissive layer, green. It has Hall transport layer, yellow. It has electron transport layer, red. It has electrodes. And it can cover, if you properly work with perovskite, all the gamut, all the colors. This is the black triangle, so it is good material. There is the good review. This is usual, multi-layer LED, not single layer. So why we need so many layers? In fact, there are more layers, not only three. They have so-called injection layer, electron injection and hole injection, additionally to transport layers. Why is that? Because you need the electron to jump from cathode of your electrode. It should be low work function. It jumps to electron transport layer through the injection layer. Then hole from the high work function jumps into the hole transport layer. And then they both injected into emissive layer, which is our perovskite. Then they meet here, create exciton, and exciton creates light, photon, which we are happy to celebrate today. All these photons come with very nice narrow line, beautiful colors, but if we will not inject these carriers, it will not work. We need to inject them efficiently and without problems. And we need electrodes which are stable, not these special ones with low work function, high, any electrode, like in this LED on the top. For that, we created single layer device. Look, in single layer device, anode and cathode can be of any material. Inside, it is complicated. It is not only perovskite. It has additional ions and it has a little bit of polymer, which is polyelectrolyte. When we apply voltage, these ions move, not only electron and hole move, the ions move. Of course, it takes some time, but it is reasonably small time. And they create the layer at interface, which creates this electrical field, high interfacial electrical field. It helps carriers to get inside. But it is not only high interfacial electrical field like in usual electrochemical devices. Because our material is semiconductor, when the ions move, they create p-doped region and n-doped region. This was absent in other types of electrochemical devices because they are made of salts, complexes. This is best semiconductor. So when ions move, they do doping like in silicon. So we have two effects, high interfacial field and doping. And then the emissive layer is in the middle. It is PIN structure. Emission comes from intrinsic I level. This is the whole thing. And these are the design parameters which we use to design these devices. So you see, I'm comparing multi-layer OLED, which has 5 layers. And this is our LEC, it has only 2 layers, not even 1 layer. And when we apply electrical field, the ions move and they create the interfacial field. And I said it is more than that. So instead of having these additional layers, we have only 1 layer, which is very simple, useful. And what happens when we apply electrical field? You see all these ions, which make the lattice. They start moving and they collect at the interface. At the interface, there is layer, 1 layer atomic creates electrical field. There is area that creates PIN junction. And we published all that in nice papers. And these are the materials which we can add. So one of the materials which is important is, I will show you what the active components. Perovskites, of course, is active component. We add it through some, but then there is ion conducting polymer. It's called PEO, polyethylene oxide. We add a little bit, maybe 5%. Then we add lithium F6 salt. How much? Nobody knew how much we need to add. So my student, Allah Bakshi, did many experiments and he found that only 0.5% is optimal. You see, this is 0.5% and he see maximum in the light emission and he see best improvement of IV characters And you see very bright 15,000 candelas per meter square, which is very bright. Usual screen is about 100 or couple hundred candelas brightness. And then Aditya Mishra did study of the lifetime. This is the time in hours. So if you this usual time transfer to time instead of 3,000 candelas, at 800 candelas, it can work 100 hours, which will extrapolate to 6,700 hours at 100. Usual screen. The usual screen will be stable for about 6,000 hours. Still not very stable, but this is a big progress. Usually the thing is unstable and maybe in 1 hour or less. So we were able to make it stable because of these additional lithium ions. Okay, and the optimal device properties are at only 0.5% of lithium salt. So this again shows what happens. Inside there is only one layer, but I told you it has not only cesium ions moving, which are the size is bigger than lithium, but small lithium ions, they move very fast. How we know? We made experiments in time. There is dynamic capacitance spectroscopy. We see how capacitance changes, and we see by time which ions arrive first. How we know this? Because the current keeps increasing. The injection current, in usual devices, it is stable. In our device, it keeps increasing. In short time, it increases because of lithium ions move. Then, next time scale, there is doping, which I told you. And at the next time scale, there is formation of the internal PIN structure and improvement of the whole system, which was carefully studied. And you can actually look in the papers. You see, we have found that the structure of the lattice size slightly decreased because all the emptinesses which existed there initially. It is not stable material, it is not well ordered, so we get much better ordered material, and the luminescence keep increasing. And this is complicated structure of that single layer. You see, it has perovskite, which is green. It has PO, these little lines, these are molecular chains. There is interface, and there are these little holes, these are ions. These are all ions that move and create electrical double layer interfacial layer, and there is the doped layer here. There is the same thing here. Electrical double layer, but this is P doping. So these little squares are PF6 ions. You say, oh, this smells chemistry. This is not semiconductor physics. It is, but it is semiconductor physics of ionic semiconductors, which we want to make stable. So we need to take into account the ions. It is like in our bodies, in our cells, the ionic exchange, sodium, potassium, chlorine, that is extremely important. The ions go into the cell, out of the cell, through the membrane. So the modern devices which create light, they are becoming more and more look like the living cells. Because it's not only electrons and holes, electronics, that play a role to create photons. Remember Hassan Mandel said, oh, we need electronics, and now we go to photonics, because electrons recombine, they create photons. Now we need ions. So the whole field is called ionotronics. Ionotronics that is combined to integrate it with photonics. This is how complicated it can be. And okay, this is the blends now. We call them blends because they're mixture. And you see the photoluminescence efficiency in different atmospheres was this. In air, it is actually much better. And you see it increases a little bit when we add a little lithium. So lithium improves not only the stability, it improves the efficiency. And the lifetime changes, you see. It is very fast decay if there are no lithium ions, and the decay becomes slower. We did this photoluminescence transient spectroscopy, and this higher photoluminescence quantum efficiency, fewer traps. Ions looks like a trap itself, but it is not. It improves the traps. And the X-ray shows that we actually improve. We create stronger bands and we reduce crystallite size. Okay, and we improve the crystallite order because of this, because it eliminates the empty space. And this is just schematic vision why we improve the stability. Lifetime, which is stability, in usual device, our own ions move. And in lithium LED, the structure is preserved, but these additional ions, blue ones here, you see, they move and they preserve. So only 0.5% is needed to screen the electrical field. I understand that all of you are students of the first, second, third grade. You know, electrical field penetrates into the material. But if we will create the screening layer of ions, electrical field will be screened. It will not go inside. If it is not going inside, there is no electrical field inside that can move the ions of the material itself. So we use the small ions, they go, they screen, and inside there is no field, which is good. The field is on the interface, and that is good for injection of electrons. So we gain double. We preserve the material and we improve the injection at the interfaces. Now what we did, this is, we took the material, look, which is ionic, and it is a guest, iridium complex. Iridium atom in the middle and big molecule around. But this is ion. We put it inside as a guest into the host matrix. And now we have two lines. This is emission of our perovskite, and this is emission of the guest molecule. And depending on concentration, we can have mixture now of two colors, green and orange. Mixture of two colors gives us all sorts of colors. And additionally, these iridium atoms, they also move in electrical field. And when they move, the area, the active area of emissive process also moves. What happens? Because of that, we can move. Okay, this is how it depends on the percentage, the colors. This is green color of cesium, this is the guest. Now we have combination. And of course, combination of colors gives us different nice colors. And the colors can be from green, yellow, orange, red. All of them. And at high concentration, we can control the colors by external voltage. You apply voltage of 3 volts, it is red. At 6 volts, it is again green. And we can control it nicely, so we don't need to put many layers. One layer with intrinsic colorful guest gives us different colors. Now what we did, we increased the operational stability, which I basically described, but this is another aspect of it. And then we did the pure blue color. I told you, everyone wants to have the blue color. For blue, we need a little bit chlorine here. If you will put chlorine in a usual device, which is multi-layer, and there is electrical field inside, this electrical field will start moving chlorine faster than bromine, and what will happen? Segregation. The whole crystal will segregate into blue emitting and green emitting. And chlorine actually will do violet emitting. We want to avoid it. We want the middle color, which is turquoise or slightly blue, to stay there without separation. And that was done in mixed halide material. You see, we can have different colors depending on the mixture percentage. Now, usually it segregates in electrical field. Luminescence does not segregate. We have all these colors from green to very nicely clear blue color. In electroluminescence, as I told you, in usual three-dimensional material, there is segregation. But electroluminescence of our material, we still can see all shades of blue, starting from turquoise and blue. So it basically repeats photoluminescence, which is because of the additional component, which I told you, that preserves it. And this is what people wanted to have for blue color. There were different groups doing what I already described, but this can be achieved by so-called size quantization. Size quantization means that if instead of three-dimensional material, you have layers, one layer, two layers, three layers, there is quantization like a hydrogen atom, which creates the discrete level. So if in the bulk, the band gap is this small, if you have one layer, you see how big is the band gap, because there is size quantization. Only electronic wave of certain wavelength can survive inside. If two layers, so this is violet, this is blue, this is turquoise. We can have different color without chlorine, just from the same material, making low dimensions. And we did it. Maksud was able to create, and these are the peaks, which correspond to certain layers. People did it, different groups, Sargent, Ma, you see they have two layers here. People did with a friends group, you see they can have all these size quantization layers, but the efficiency was not good. And they used only one type of, they call it ligand. You see, to separate the layer, you need these gray layers around it. These are called ligands. They separate the layers. If you use only one ligand, you cannot achieve much. Now, what Maksud did, he added this type of molecule and this type of molecule. Now we have two ligands. We mix them with our material. Okay, we get nice control of the one layer, two layer, three layers. And this is the color. You see, the wavelength is now very deep UV in photoluminescence. So this is what we can do. And also in these two-dimensional layers, the excitons, you know what is the excitons? When electrons hold before they emit and make light, they make a coupled state. It is called exciton. In usual semiconductors, excitons are not nicely coupled to each other. Electron and hole binding energy is small. Only at very low temperature they are stable. In two-dimensional perovskites, depending on the number of layers, this is binding energy of exciton. You see, in three-dimensional, it is only 15 to 50 millieV. Room temperature corresponds to 25 millieV. So thermal kinetic energy of the material, because it is at room temperature, already destroys this 15 because it is 25, more than 15. However, if you do layers, 170, 200, 400, and in quantum dots also it can be 300, 220. Excitons are very strongly bound. It means that luminescence cannot be avoided because luminescence comes from excitons. If you destroy exciton, carriers separate, they never meet again, they're trapped, and all the luminescence disappears. In two-dimensional layer and in quantum dots is zero-dimensional perovskite. We can have extremely strong luminescence, and it is extremely narrow line. So recently, and I am very proud, in Samarkand, this is the group in Samarkand, and this is example of collaboration. These two girls come from my lab in Moscow. You know, they're in trouble now, there is a war. So they traveled to Samarkand and they did master class for Uzbek researchers like you, and they were able to synthesize these nice looking, bright quantum dots, blue, green. They shine light, UV, and they see how bright the electroluminescence is. Not photoluminescence of quantum dots. It is not only bright, it is single photon source. What means single photon? Single photon means that they have special statistical properties. Each photons are absolutely identical, and that can be measured by special techniques that measures the correlation of photons. If there is, no correlation, it means that all of them are absolutely identical. And this is the reports that quantum dots can be single photon source at room temperature, because all these excitons inside are very strongly coupled, and all these narrow lines are the narrow lines of excitons in different types of perovskites. Okay? And this is already we created in Samarkand Quantum Center. Green color, blue color, different types of quantum dots. And these are the excitonic transitions which create single photon stream. There are excitons and bioexcitons, two photon emission. So this is the future. This is the future of this field. This is the correlation function, which is called G2. This is the ideal single photon emitter. It should have very small correlation function and very small radiative lifetime. The best gallium arsenide, other materials are here. Where is perovskite? Already here. You see, it is below and better, closer to small correlation. Then gallium arsenide. Gallium arsenide actually is now the best. But there is gallium nitride here. It has good G2, but it does not have enough radiative. G2 is not good. It should be 0001. It is 100 times larger. Perovskites are better, order of magnitude. So basically, we are working on this. And now we need not only photon, we need electroluminescence. For electroluminescence, we mix them into the body of the three-dimensional material. So this is a mixture of three-dimensional plus quantum dots. So that's what we did. It is mixture of 3D and 0D. Composite. 3D has this composition, usual cesium Pb bromine 3. This is cesium 4 Pb bromine 6, because this is quantum dot. Okay, and we put different amount of quantum dot, and we see there is maximum of photoluminescence quantum efficiency, and there is the lifetime optimal when we mix quantum dots in a certain amount. That's how it is done. And now we mix 3D, 0D. They are all in the one single layer device, which we like, as you understand. I'm always speaking about single layer. This is how they look like, and this is the beautiful spectrum of the very intensive. You see, without quantum dots, it is here. We mix quantum dot, it goes up, up, up, with zero-dimensional quantum dots. And also this shows that we can improve the characteristics, mixing proper amount of the quantum dot. So inclusion of quantum dot into 3D matrix improved overall device. And the currents are good. It shows that the lifetime, half-lifetime improved. This is without quantum dots, which is with quantum dots. Okay, and that is measured by so-called electrochemical impedance spectroscopy, which I understand you are not experts, but I will not get into the details. And the crystalline structure also can be improved. Now I am coming for fun part of my talk. Now I want to show you the experiment and give you this magic, beautiful material, which I want to pass. There must be the light source somewhere. No, you don't need gloves. You can give it to people and they can watch the beautiful, how beautiful can be photons. No, it's okay. It's bright enough. So this is synthetic photonic crystal. Look at the reflection. These are called flashes of fire. Yeah, give it to people. This is porous material. It is made of little spheres. Look, these are little spheres, and they are periodic. And what you see is made of crystallites, which you can see by your eyes. And when you shine light, photons behave like electrons in semiconductor. Conductor cannot penetrate into band gap, right? They can exist in valence band, in conduction band, but in forbidden band, they do not exist. Same thing with the light there. You put photons, the light color, when they do not penetrate, reflected into your eye. And you see beautiful red color, green color, blue color. That is photonic band gap. There is band gap for the energy of the light. Why you want it? Because at that wavelength you can make a laser. Because the material is a mirror from inside by itself because of the Bragg diffraction. This is distributed Bragg reflector. If you take distributed Bragg reflector, it is like a waveguide. What you can do, you can insert quantum dots inside. These quantum dots we can put between that spheres. And we can create quantum dot laser inside that material. In that case, you do not need the torch from outside. You put quantum dots, you put electrodes, apply current, voltage, and the light will start coming from that piece, like a beam, like from your pointer, laser pointer. So you can be able to make new type of laser pointers and powerful lasers for photonics. Because what is photonics? You have photonic chip, it has light source, it has line where photons propagate, optical fiber, and at the end it does some sort of processing, microphotonic chip. Light source can be that type of laser. And this is my paper in Science, which shows that we start with periodic lattice of what you have in your hand. That is called porous photonic crystal. It has spheres. Spheres are connected. This is the sphere. And yellow is inverted opal lattice. In usual material, it is filled with air. But we can fill it with something else. We can fill it with quantum dots. We can fill it with polymer. Look, here, the sphere remained. What we did, we dissolved the spheres. The material which you have, if we will put a droplet of hydrofluoric acid, it will all disappear. In our case, all the spheres disappeared, one remained. And we filled with some other material, polymer, carbon, metal, perovskite. We are trying to do perovskite. Then we will have inverted opal. Direct opal, inverted opal. Inverted opal has much brighter color. It does not need liquid. It does not need any. It's already very shiny. It looks like this. Sorry, I did not put that picture. I had the picture from the Science magazine cover. It's a very bright, colorful image of the inverted opal. So this is the challenge. Now I already moved to the challenge. This is the challenge for my Samarkand Quantum Center. Girls come, they taught them to make quantum dots. I am bringing photonic crystals to Samarkand, the one that you have. I met them in the company in America, and now in Samarkand they will be making more. They will slice them, infiltrate with opals, and try to create unusual single photon quantum laser. That's what Hassan Mandal mentioned today. Lasers are already quantum. Right? What is laser? Laser is light amplification by spontaneous stimulated emission of radiation. Laser. It is quantum effect. But quantum laser, double quantum, means that the emitted photons should have the statistics of special type. They are single photon source. Nobody was able to really make a good single photon laser or quantum laser. That is the dream for quantum photonic computer, for quantum photonic communication. This is one dream. And we have this device, which is called nano imprinter. Instead of making opals, you can imprint these things at the nanoscale in this device, but it will be not three-dimensional. It will be two-dimensional grating. And we can make them, and we are doing them. Anyway, now there is another field. I will quickly mention it. You see, the papers start appearing about memristor. You see, memristive photosynapse. It can be together heterojunction diode, photovoltaic cell, photodetector, and memristic photosynapse. People are trying to make devices which look like synapses in our brain. Synapses in the brain, they transfer the neuron. There are this whole thing is called neuron, and synapse is the connection of neurons where the signal goes through when you think about something or create memory. That thing works because these little ions inside, they go in, out, and synapse either opens or closes, on-off function of the usual transistor. So our neuron nerve cells act as a so-called neuromorphic network, and we can use this memoristic behavior using the thing that was created, suggested by the guy whose name is Leon Chua. You know that voltage is connected to current through the Ohm's law. Voltage is connected to charge through capacitance. Current is connected to the magnetic flux through the inductor. So we have resistor, inductor, capacitor, right? Elements of the circuitry. But one is missing. What is missing? This connection. There is no connection of charge and magnetic flux. You can say that dF, the differential of flux, is proportional to charge through something which is called M. M is memoristor. It is memory resistor. This is memoristor. Memory resistor, if you take into account that M is dF over dQ, you integrate both parts, you will get voltage divided by current. This looks like Ohm's law, right? R is V divided by I. But this V and I are time dependent. So this is time dependent resistor, which depends on the dynamics on the memory. So the memory in our brain and all other memory things are related, maybe, with properly created memoristors. And memoristor, this is example of memoristor. When you start applying voltage, there is very low resistance. This is IV. At certain point, it jumps and then it goes back at high resistance. So there are two, low resistance, high resistance, two states. That is because the doped area between electrode in, for example, titanium oxide, it moves. When it is not doped, it is low resistance. When with time it becomes doped, it is better conductor, so it is low resistance. So everything depends on the movement of ions, which dope or undope. When they dope, resistance change. That is the effect of memoristor. You see, there is not doped area, and it has two states. Oxygen ion motion is the key for memoristor behavior in titanium oxide. And I was all 1 hour telling you about ions moving. In our case, it was not oxygen, what it was? Lithium. So when lithium moves, it changes our LED device. In the beginning, it is not bright LED, then it becomes bright LED. In the beginning, we need high voltage, and then it becomes low voltage. So there is memoristic behavior, but not for resistance, for photons. This are MEM diode, which has memoristic LED. And look, when these ions are still here, we need high voltage. When ions already collected, it goes back at the lower voltage and different brightness. Here, brightness at this voltage is very low, and here very large. So there are different brightnesses. And this is what was done by actually my son. He has hysteresis in light emission here and here because of this high electrical field. And if you will apply the AC current, you can see the different type of dynamic behavior depending on the frequency of the applied voltage. Anyway, I will stop here. This was the paper published. It was called Light Emitting Memristor. Light Emitting Memristor, but it was without perovskite. It was in older days. Now we are trying to do it with perovskite. And it shows that neuromorphic computation depends on training, learning, the synapses and voltage-dependent response between synapses is what happens. Anyway, I will go through now. This is our Samarkand Quantum Center. Samarkand Quantum Center is in Samarkand University. It has already 7 groups. Superluminescence, chemical synthesis, magnetic behavior, photoelectrics, and so on. And we want to create elements of quantum circuitry, polariton qubit, spin qubit, single photon sources, spin LED. All these are new types of quantum partially photonic devices, which we are trying to create in Samarkand. So with this, I want to stop my already 5 minutes exceeding time presentation. And I want to welcome you, and this is our roadmap. You see, these are usual devices, and these are quantum devices, which we want to develop using smaller dimensional perovskites, starting from 3-dimensional, 2-dimensional, 0-dimensional wires. We incorporate them, and hopefully the perovskite story will keep developing to the quantum field. And this is my Turkish colleague. His name is Volkan Demir. Volkan Demir got a mega grant in Bilkent, Turkey, and in Russia, in Petersburg. But that already finished. This is a new thing. For 2024, there is new mega grant announced. So maybe we can collaborate with your Photonics Center, create a mega grant. Maybe we invite Volkan, he's in Singapore, or some other scientist, and we can get quite sizable funding, because scientists need funding. This is mega grant announcement for the new period. If you have any questions, I'm open to discuss that. And I'm here for a couple of days. Tomorrow evening, I'm flying to Samarkand, and I invite all of you, Hassan Mandal and Aziz Sancar, whom I devoted the talk. They are coming in December. And in Samarkand, there is a center of Aziz Sancar, I told you. In my quantum center, we are trying to help Aziz Sancar. Because what he did, he used photons to control the DNA in our bodies. DNA damage creates cancer, and we want to stop it with proper photon control. Thank you very much. Yes.
Yeah. My question is, how uniform can you manufacture these quantum dots? How uniform can you manufacture?
You know what? Quantum dots, surprisingly, and that is the magic because of which they got the Nobel Prize recently, 2 weeks ago. Bo Wendy got the Nobel Prize. When you make them, because everything happens very fast.
Yeah, if you don't mind, let me complete my question.
Okay.
Because as you mentioned, the indistinguishability of the photons, right? Very critical in quantum optics.
Right.
And that depends on the uniformity of the geometry, of quantum dots. And usually in manufacturing, there are changes in sizes, and that makes frequencies, shift a little bit.
That's good. That's a very good question.
And if the frequency is different, then you don't have indistinguishability.
Of course not. Of course not. We need exactly the same frequency. And you know how it is done? The process of making colloidal quantum dots actually makes them with 0.5% deviation. Still there is deviation, because with two syringes in certain temperatures you make them. Still we have sometimes distribution. So what we do centrifugation, and only the certain size remain, others go, or precipitate. And also we can use the filtration. And of course in perovskites it is more difficult to get same size. This is a problem. But there are other problems there.
What is the maximum spread in frequency you should have?
Spread in frequency, right. You want to have zero spread in frequency. And that does not directly relate to the size. Sizes can be a little bit different, but quantization levels still same. Quantization does not exactly follow the geometrical size. We can discuss that later.
Yes, yes.
You know,
Because if you solve the Schrödinger equation, right? It's like a quantum well.
I know, but the energy levels, the formula is simple. H squared pi squared divided ma squared. A is the size, but the size is like a diameter. These things are not complete spheres. They are single crystallites with their own shape. So that quantization depends plus minus, the size in that thing does not give big spread of discrete levels. At least that's how I understand it. But maybe we need to be more precise in making absolutely same size and same composition. But even without, okay, other question.
Thank you very much for your presentation. I have a question about the single layer. I'm not familiar with the perovskite, but the
Can you speak louder so that I understand?
okay. I am not familiar with the.
Maybe give another microphone, because
That doesn't work, I think.
For the channel.
Can you hear me now?
yeah, I can hear.
Okay, I have a question about the
Single
single
layer
layer.
device.
Yes, I am not familiar with the perovskite, but the OLEDs. In the OLEDs, it's easy and efficient way to create light in the single layer, but there is a problem when you do that, because you should have think about the for example charge balance or the electron hole mobility or other things or
Right.
other yes and
But the most important is injection.
yes
You cannot inject in single layer efficiently if there are no injection and transport layers.
yes I think you maybe I missed that, but I think you didn't do that. Did you use whole electron transport or electron?
No, in perovskite we do not need it. In perovskite we have just one layer,
Mhm.
and because of the internal movement of ions, the external layers become p-type and n-type because of doping. In organic materials you cannot do internal doping.
I understand. I think you don't have to think about the charge mobility, charge balance, or other things
Look, charge balance comes automatically.
automatically.
Automatically,
Okay.
it's self-balancing device, because there is self-doping. Self-doping self-adjusts the levels,
Mhm.
and even the level of the, for the organic you need high work function, low work function. Here work function does not matter,
Okay.
because work function pins itself with the Fermi level of the doped layer.
Okay.
Very different thing than organics.
Thank you very much. Another question. Okay. Thank you very much.
We can discuss that because people tried to do in conjugated polymers, single layer, Higger group and others.
Is hysteresis behavior depends on the frequency of the applied source in perovskite.
Frequency of applied source for what?
The hysteresis behavior.
Yes, exactly.
It depends on the
Depends on the frequency.
depends on the
In the
frequency.
memristor.
Memristor, yeah.
Yes.
And how about the stability? You stabilize the hysteresis behavior, right?
That is not solved yet. This is a challenge for us.
We had bought a memristor 4 years ago with my PhD student.
Really? Fantastic.
That was built on titanium dioxide dynamics, and it was not stable.
Yes.
We couldn't achieve the stability.
Look, that's why I'm happy that there are people who understand memristors and their frequency dependence. Maybe we can work together on that.
Actually, in 2004, the Leon Chua visited our institute because I arranged an international workshop on nonlinear dynamics.
Wow.
And he is a pioneer of the nonlinear dynamics.
News for me that you already were doing.
Yeah,
but you did memristor, which is not light emitting memristor. It is usual memristor.
Yeah, that
resistance.
Is, yes.
I'm speaking about next step. Memristor diode.
Yeah, I understand.
Memristor diode is even more complicated because now the photons are involved.
Mm-hmm.
You know, so maybe that will bring you additional parameter for optimization of nonlinear dynamics.
Probably, yeah. Thank you.
Yeah, I will be happy to talk to you about that thing.
Maybe it's better to, okay. Thank you very much, Anvar. It's been great for us to host you here in person, and I knew how good teacher you are, but I'm really happy that our students can also benefit from that.
Thank you so much.
So as far as I understand, the LECs, the light emitting electrochemical cells, are actually using the knowledge that has been used in DSSC technology in dye-sensitized solar cells, changing the size of the ions, and you're also using the hexafluorophosphate,
right,
and tetrafluoroborate.
Same ionic salts.
So the ionic salts, it's not just chemistry or not only semiconductor physics, but it's photonic material, the science of photonic materials, let's say.
Right.
Have you ever tried TFSI as a larger ion and how it would affect? Because those were the three most popular
Of course,
ions.
I remember. Yeah, this is excellent question. I will send you the papers where we do it, and these are parts of ionic liquids.
Yeah.
TFSI, for example, right? DEME TFSI. Yeah. There is DEME plus TFSI minus. This is very strong ionic liquid. We used DEME TFSI, BMIM TFSI, all these ionic liquids in photocells, not in LEDs. In LEDs, I did not have good student who can make LEDs still working with this type of bigger ionic salts.
I see.
Yeah, because LED needs higher voltage, like 6 volts, 5 volts. So something was happening to bigger ionic molecules. Photovoltaics works at 1 volt, half volt. We do not apply voltage in photovoltaics. So for photovoltaics, it was okay.
Yeah,
but this is excellent question. This was last line in my talk today. External ionic liquids in devices.
Yeah.
This was done some research in photovoltaics, but not in LEDs.
Yeah. And
it will be nice to extend it to LEC.
But depending on our experience at lab, although we say that OLEDs does not produce heat like the LEDs does, and also the QD LEDs are also very innocent on producing heat.
Right.
It's not always the same. I mean, whenever we use the camera, we obviously detect the heat
You detect
change.
the heat, of
Yes.
course.
How about your dimmable device that you dim it and you gain from green to red? You have shown in your slides. What about the heat that heat change occurred? Because that would also have a lot influence on the stability.
Right. I honestly say that was not studied. This is very new research. We did not go to heat yet. I think there is heat generated, of course. And that heat probably decreases the stability. So this is something to study additionally.
Device architectures. Thank you
Right.
very much once again.
Thank you. Thank you very much for being patient for my very long talk.
He leads the Biophysics and Medical Devices Lab, showcasing expertise in biophysics, biofluids, and microfluidic devices. Join her webinar, Optical Trapping in Biomedical and Biophysics Applications, as she unravels the secrets of optical tweezers and their applications in controlled experiments. Please join me in welcoming Dr. Viviana İZPHOTECH to share her profound insights.
Done by Charles Downs, creating an intense, precise beams of coherent radiation of microwaves named maser. That led to the later creation of the laser, first demonstrated by Theodor Maiman in 1960. Arthur Ashkin was the first to realize optical traps in the early 70s. Ashkin and colleagues reported the first observation of what is now commonly referred to as an optical tweezer, a tightly focused beam of light capable of holding microscopic particles stable in 3 dimensions, as is shown here. So in this case, we have this focused laser beam. There is a laser beam here. There is a lens just in front of it. It's a very simple experimental setup. This lenses is allowing to this laser to refocus on a focal point, and then there is a particle located in this point that is levitating in the air due to the trap forces. So by means of optical tweezers microscopy, objects can be trapped via high focus laser beams, as I'm showing here. And they are called as such because this object can not only be trapped but also moved in a controlled manner. So with these traps, the electrical particles as well as living cells can be manipulated. And the outstanding advantage of optical tweezers is especially for biological purposes that mechanical forces are not exerted onto the cell. So contamination of the investigated cell can be excluded a priori, but it will of course depend on the experiment that we are performing and the method that we are using as well. All right, so I will talk a little bit about the theory. So different theories concerning the theoretical description of the optical forces acting in optical tweezers have been developed for different sizes regime of the trapped particles. But in general, so we have that, I mean, this is a very, very basic, but still I think worth to mention that we have the absolute value of the momentum of an electromagnetic wave that is determined by the energy of the wave and the speed of light according to this equation. And then we will have like a very basic change of momentum will be characterized by these equations here, where we relate the change in energy in time with power of radiation, and this will lead to a force. So then this is very clear from this that coming from the radiation power of light, we can actually exert forces on objects. But then we are going to talk a little bit more on detail. So for different regimes, So we have this ray optics model where the diameter of the particle is much more bigger than the wavelength of the laser that we're using. And in this case, we will see that it's, well, this ray optic, so the basic operation of these optical tweezers can be explained by the momentum transfer associated with the redirection of the light as the electrical interface. There is the particle here. So in this case, so we will have that, for example, we have a ray of light that is banded into this particle, and it's going out in this direction here. And we have two different sides width representing the intensity or the number of photons that are hitting our object. And in this case, of course, since we have this intensity profile, so we have a gradient of laser here, so that's much more intense in the middle and less intense in the borders. So in this case, we will have that much more transfer momentum. It's exerted by this ray here compared to this other one. So since the laser is changing the direction into this, to the left in this case, so we will have finally, and this is going to the right. So we will have a momentum exerted into the particle due to this ray going to the right, and then due to this other ray going to the left. But since we have much more contribution of this one, so we will have a net force that is acting to the right, so pushing this particle going into the middle of the trap. In the case that we have still the trap in the middle of this intensity profile or laser beam, we'll still have this net force that is going into, that is making advance this particle. It's just because we haven't focused yet this laser beam. So in order to get the particle trapped in the middle of this laser, so we will need to get a laser that is focused as we're showing here. And with this focus laser, we will have, again, a gradient of intensity going to the middle. And then this is creating a net force, pushing the particle into this focal point. That will happen also if we put the particle far away, further to the symmetrical point of this focal point. So then the resulting would be that we are going to have our particle as we were showing in the previous video. But then we will have still there are multiple, if we take a look on detail, we still have multiple refractions and transmissions inside. And then we can calculate with all this our force due to the gradient of pressure, and then our force also coming from the scattering. The scattering is coming from this radiation force into the particle. And this will lead to this expression of net force on the particle that will be summarized by Q, that is called quality factor, and then our intensity of laser divided by C. That is velocity of light. And these quality factors have been measured regarding to the angle of incidence of these rays going into these beams. And we can notice here that they are maximum, or they get a maximum value at around 70 degrees, more or less, around. So it means that if we would like to maximize the force on a particle, we will need an objective with a high numerical aperture. So this is more than obvious, taking a look on this. So in this case, since we know that the numerical aperture is depending on this angle, so if this angle we would like to be very going into 60 or 70 degrees, so we'll obviously need this numerical aperture to be a high number. Then we have another approximations, the Rayleigh approximation, where the diameter of these beads are much less than the wavelength of the laser that we are using here. In this case, the particle is, we can approximate it as a dipole that is interacting with the electromagnetic field of this laser beam. And in this case, anyway, we'll still have a gradient of a force that is pushing the particles towards the middle of the laser focal point. And then we will also have our scattering. It's just that the equations are different from the rate optics. And then we will have a middle approximation that is called Mie approximation. It's when the diameter of the particle, it's about the wavelength of our laser beam. In that case, we also have, let's say, very complicated approximations of which are the gradient and the scattering forces. So in that case, well, I just decided to skip them. So holographic optical tweezers. So previously, it's just the basic concept of how can we trap a particle. Something that I didn't mention in all my speech was that it's very important, but I just show it here. Sorry to come back, but the refraction index of the particle should be bigger than the refraction index of the medium. If this is the case, so then we will have our particle push towards the middle of the high intensity of the laser beam. If this is not happening and the refractive index of the particle is less than the refractive index of the medium, so then the particle will be actually pushed away. But it's anyway, in some applications, this is also useful, but in the applications that I will talk, we're going to stick with this other case. So then, holographic optical tweezers, they use these computer-generated holograms to create arbitrary configurations of a single beam optical traps, and they are useful for capturing, moving, and transforming objects. So by a combination of beam splitting, we will have an adaptive wavefront correction. And they can be also exert precisely specified and characterized forces on objects, ranging in size from a few nanometers to hundreds of micrometers. So what is the principle of these holographic optical tweezers? So we have light. We know the light, of course, aside from the frequency that determines the color. So possess another further important parameter, so the amplitude and the phase. And if we would like to characterize this object in pretty special configuration, so we need to take these two last parameters into account. So the central to the hologram generation is this so-called phase modulation. And this phase modulation is achieved with a so-called phase modulator. And in this case, well, I mean, talking about is what I have here. This is a configuration that I was using in the lab when I was working in Germany in Saarland University. So here we have laser used for realizing the optical tweezers. So diode pumped ND YAG. So this one, that's a solid state laser. And that works with a wavelength of 1064 nanometers, and with a Gaussian, let's say, profile. And then this laser, for just for purposes of alignment, we have this other laser of helium neon. So just to simplify the adjustment of the optical tweezers. So so we have the power supply that was outside another table just to avoid vibrations. And And then after we have this beam expander that allow us to have the beam expanded up to 20 millimeters in diameter. And all the optics were coated with the anti-reflection layer designed for this wavelength of 1064 nanometers. So with the help of several mirrors, optics, the laser is directed into this special light modulator that we have here, this PAL SLM. And the heart of this actually holographic optical tweezer is this PAL SLM. So it's this is accounting for this parallel aligned liquid crystal spatial light modulator. And so the intensity distribution of the grading laser is modulated over an electronically addressable liquid crystal display. So we have this XGA signal of the phase hologram applied to the LCD via an output of the graphic board of the controller computer that's connected to the system. So the intensity distribution of the grading laser arises through interconnective optics over a layer of amorphous silica that we have here in the actual PALM SLM. And the special filter of the connective optics remove higher frequencies and the pixel structure of the LCD and can be minimized. So then we have this dielectric mirror, this sandwich between the liquid crystal and this and the silicon layer in order to enhance the reflective performance of the device and couple with various of the readout of the light wavelength. So the liquid crystal, its directions are all parallel to each other in the PALM SLM. And the application voltage of the molecules simply tilt with essentially no rotation about the optical axis. And this causes a phase modulation of the light polarized along the original direction of the director, while the orthogonally polarized light is essentially unaffected. So then we have that the ND JAG laser is reflected on the dielectric mirror. And and we will have that at the end, the modulation of the phase will depend on the voltage that we are applying here. So this is a picture of this modulator that we were using in the lab. And these here are pictures of this phase that we were controlling with the voltage through a program. And what is interesting is to see that finally we have here a configuration of the laser beam. In this case, we have divided the trap into four independent traps that we can also separate and control the distance between them. So here we can see that we have different numbers. So 4 traps, here we have 2 traps, here we have 4 traps, but as you can see, changing the phase, so modulating the phase, the voltages, we will have, or we can have different configurations of these traps. So now I will talk about a little bit of applications, but I will be a little bit more make a reference of what I was working with or what it's my area of expertise. I used to, and I still work a lot with blood research. So for those who are not familiar with blood itself, so what's blood? We all know how it looks like. But if we take, for example, this full tube with blood and we let it sediment, we just don't touch the blood. Let's say it is a simple case, and we just wait very long enough. We will see that the red blood cells that are inside are sedimented and they are actually phase separated. So we will have At the very bottom, the red blood cells, and then we will have in the middle white blood cells and platelets, and at the top we will have plasma. So this is the main constituents of blood. So 55% will be plasma, and the rest 45% will be the red blood cells. And from these 55% of plasma, 93% it's water, and then the rest will be proteins like albumin and fibrinogen. And then from these 45% of blood cells, we will have 99% will be red blood cells. So it's a very high quantity. And then only 1% will be white cells and platelets. So blood is performing several functions in our body. Some people see it as a moving organ, that it's performing different functions, like for example, it's the one who is keeping us safe from pathogens through this immune system. It's also regulating our temperature, our pH. It's also delivering oxygen to all our tissues. It's also releasing the wasting products as CO2 to the environment. It's also the place where hormones will be distributed, nutrients. So it's actually extremely very important organ in our body. But it's also the place where if we have a cancer growing up somewhere, it will be the place where these little cells will be transported to all the places, different places of our body. So it's also something that cannot be very good for us as well. But I mean, I will focus first on this thrombus formation. So if we have an injury somewhere, so there is something that is called this cascade of coagulation cascade. Maybe some of you have heard about that, but it's basically that in this case, we will have, if we have an injury, so the platelets will be activated, and a lot of factors, I mean, not only coming from platelets, but coming from the endothelial cells will be released to the bloodstream. And then a cascade of events will start to happen. Like, for example, the fibrinogen will start to transform into fibrin, that are these fibers here. Platelets, they will start to stick to the vessel walls, to cover them, to cure this injury place. And so obviously platelets are really important in this process because are almost the first ones to be activated, and these are activated in thrombin, and a lot of things are happening there. But red blood cells, for example, they were believed to, since we have so many red blood cells in the blood, they were believed to play a passive role on this thrombus formation, that at the end it is clot that it's covering our injury. But however, there was some propositions from some groups that they were saying that when the platelets they got activated to initiate this cascade event, they were releasing some of these that is called PGE2 and LPA. And then when they were releasing this, so the red blood cells finally, through a, let's say, process, they were getting some of the lipids that are called PS in the outer leaflet of the red blood cells. And then this will lead to finally that they become a little bit more adhesive. And then since they become a little bit more adhesive, so they will, let's say, aggregate. So if they are aggregating because of this addition, it means that due to the activation of the platelet, so red blood cells are not exactly a passive object that is just trapped into this mesh of fibrin that is formed in the cascade when we have a clot, but they could actually play a role on this, creating a little bit an even more stable clot. So why I'm talking to you about that? It is because optical tweezers actually are a very useful tool to check, for example, to manipulate red blood cells. So in this case, for example, this is the case that it's the second row. So we have 2 optical traps, and then each of the traps, it's trapping actually a red blood cell. As you can see here, this is a video that I did a long time ago, and they are getting aligned with the laser. The laser, they have such a small intensity that they are not burning out the red blood cells. So this is very advantage for this biological system. And on the other hand, it's allowing me to, as I told you, change the distance dynamically while I'm configuring this through a computer. So basically, manipulating these objects that in this case are inside a microchannel, so I can perform some experiments and combining them also very interestingly with the microfluidics. So in this case, to explain you what was done here, so we have a microfluidic system where there is one of the channels that is enriched with this LPA liberated, secreted by the platelets. And then in these other channels, we will inject red blood cells. Red blood cells, they will come here. This is a quasi-static flow anyway. It was not like the before where the cells were like flowing away. So we have these 2 red blood cells. Each of them, they will be trapped with the optical tweezers. And then since we are in a very low Reynolds number regime, so it means that there is basically no mixing between this upper layer and the lower layer, or the mixing process actually is happening, but it's happening very, very, very slow. So what we can do is to have a place where the medium it's without this factor, and then in the upper part we put this that is in our interest, and then we move with the help of the optical tweezers these 2 objects to this other channel. So once we have done that, what we can do is, so actually this was use 4 traps. So we will have one here, another one at the bottom. So holding one of these red blood cells to have it parallel to this other one that is also held by 2 traps here. And it's we can approach this cell, as we can see here, and then we can push it back. And then we can repeat this process several times. And then there is a point where we will see that actually the cells, they are showing addition between them. As we can see here, there is also a very strong link at the bottom. So by using these optical tweezers, we can evaluate if there is or not addition among red blood cells in this case. And the conclusion of this work was that actually there is a big percentage of red blood cells that are becoming adhesive and actually showing adhesive properties by the using of this technique. And at the end, this was an important paper, a breakthrough, because it was believed that the red blood cells, they were not playing a role on this cascade, but actually they were, because of this addition activation. So another example, it's this, again, going with the red blood cells. So you know that if you have the red blood cells, and if you don't have any of these proteins around, so they will just
So they applied.
This is an image of under a microscope of red blood cells that they are just sedimenting and going to the bottom of becoming adhesive and actually showing adhesive properties. But then by the using of due to the presence of the proteins around, they will at the end that they adhere and form these structures that are called rouleaux, and then they will form even more 3D kind of rouleau structures. So addition of the red blood cells everywhere. So with the same technique, we were trying to attach two of these red blood cells and to push them away, and we were trying to, quantify the forces using optical traps among these red blood cells. So not only evaluate qualitatively if they were adherent or not, but in this case, we also wanted to measure forces among the red blood cells. So, but we know that if we calculate the forces, it's actually ranging of 150 piconewtons. That would be like kind of the limiting if you don't want to increase the intensity and burn out all your system. So in this case, the adhesion forces, they were so strong that actually optical tweezers, they were not a suitable tool to make these experiments. So instead of that, just to show you here, we should switch to another technique that is atomic force microscopy, where at the end on a cantilever we were attaching one of the cells, and then on the base another of the cells, and then approaching them one another, and then separating them and from the curves of this AFM, getting the forces between these red blood cells. So then we have a limit, and then the limit is which are exactly the forces that the optical trap can hold between the objects before be released out. So another concern about again red blood cells, it's so we know that the membrane of the red blood cells is really flexible. So we have different modes of elasticity. So for example, so the layer or the membrane, it's formed by a bilipid membrane, and at the bottom we have this cytoskeleton. So we will have a bending due to this bilayer. Then we will have this monolayer slipping here as well. But then we will have also contribution of a simple shear. But the simple shear is not happening because of this bilipid layer that it's... Hello? Come back. I didn't know what happened. So I was saying that this simple shear here will be due to this cytoskeleton that is acting as a kind of elastic layer. So not due to the bilipid layer that it's more a kind of a liquid that is not exerting any opposition to this movement that it's in this direction. So we have a flexibility on the membrane of the red blood cells. And one of the methods, I mean, there are many methods to measure which are this elasticity of the red blood cells. Though even nowadays, we cannot decouple these two different contributions, one coming from the bilipid membrane and the other coming from the cytoskeleton. Still, you can make a rough estimation of which is the deformation modulus of the full membrane of the red blood cells. And one of the methods is actually by using optical tweezers. So with optical tweezers, or with an optical trap, we attach two beads to the surface of a cell, of a red blood cell, and we push away. And with this pushing away, so it's possible to estimate which are the elasticity modulus of these cells. And why is this important? I mean, why it's important to know which are these modes? Of course, there are many different applications. A healthy red blood cells, they will have a distribution that will be completely different from a distribution of some infected cells, for example, or some abnormal cells in different diseases like cancer, like sickle cell anemia, like malaria. But also it helps a lot to create for the people who is doing simulations, that they actually need these elastic modes to put it inside as an input into their model. And so at the end, it's very useful to create in silico models of the blood flow. And if we have a very accurate or much more accurate in silico model of blood flow, so we will be able to model things like, for example, segregation of sickle cells. Sickle cells is a disease that is affecting millions of people worldwide. And we still don't know, for example, why this crisis that is happening in these people, that it's due to some thrombus formation everywhere. Why it's really happening, we still don't know. There are some hypotheses, but it's not full picture. People are still getting this crisis, and it's really terrible. So then we can also use the blood flow itself. So it's to characterize the drug delivery, or again, as I mentioned there, the thrombus formation. So, but then more accurate model, it will be if I get much more accurate the characteristics of these red blood cells. And one of the very famous method is really using these optical traps. So another application, I think this is a very interesting one, where you have these fibers, and in this fiber you put some lasers, and then you can exert some forces that will be, towards the other direction of the cells. So you can actually stretch cells, and then it would be kind of a similar as this one, but in this case it's less invasive, because you don't need to attach any beads to it, and then still deform some cells. So if you have, and also you can couple this. This is really interesting with a microfluidic system. Like, for example, here you have a capillary, and you can have cells passing by. So it's a kind of flow cytometry. So when you have these cells passing by, so you can elongate them, you can get your images, and then now with IA, you can also discern if you are in a control or in a healthy case, or if you are in an unhealthy case. So you can detect actually some diseases with this. So just a broad view. So you can go from a sub-wavelength. So in that case, you will need to use this approximation. So to get your forces, you will need to go for your approximation electromagnetic approximation that's talked at the beginning. And then we are in this kind of intermediate case, and we can also go for this super wavelength, so to investigate what is happening inside organism. So actually, these traps are very versatile, because it can be used not only in the case of red blood cells that I wanted to show you up, because it's the place where I feel much more comfortable to talk. But also it can be used to attach, for example, into the DNA, and to stretch DNA, and to check some mechanical properties of this DNA, or also to check some neurons, again, mechanical properties in the system, or again, going into some biological system and directly trap and manipulate things inside. So another thing, it's that you can use some beads inside some system and make also microreology. So actually, you will be measuring some rheological properties of some liquids inside some systems using these optical traps, combining this method of optical tweezers with some other knowledge. So there will be like the flow fluid of something of a specimen that you will be around. So okay, so just to make a conclusion of all these applications, so we will have that the major disadvantage of these optical tracers will be because we are limited to an optical force that will be around 150 piconewtons. So and this won't allow us to measure very such big forces that we might be interested in different type of applications. But one of the major advantages is that you can, you have of course many advantages. Already the fact to manipulate biological system with this laser, it's extremely important. It's widely used everywhere. But also one of the major ones, it's like you can easily combine it with other techniques. So such microfluidics, different imaging and microscopic techniques, but also with some other type of traps that I didn't mention here, like a magnetic traps plus optical tweezers, or some traps with acoustic waves can be also combined with optical tweezers. So at the end, they are extremely versatile. So you can have you can just become creative and to see where you are going to put it for this application that can have, depending on what you are studying, of course, can have these biomedical implications. So there's some perspective. So further advances in plasmonic fibers and wavefront shaping will be quite important for combining with optical tweezers. So of course, to get illuminated where a conventional optical tweezer system won't fit today. All right, so I will just finish here. Thank you very much for your attention. Also I got confused with the time, with the Chilean time. So just want to say that I did it, we did it. So thank you very much. And if you have some questions, I'm happy to answer.
Dear participants, I hope it was a great lunch. And it's my honor to introduce Dr. Deepak Jain, Assistant Professor at the Optics and Photonics Center of the Indian Institute of Technology, Delhi, with a stellar academic journey and significant contributions to optical science. Dr. Jain, a co-founder of Brown Science Technologies and İZPHOTECH, will share insights of next-generation optical fibers for light sources and communication. Join me in welcoming Dr. Jain to explore the transformative frontiers of specialty optical fibers.
Thanks a lot for kind introduction, and it's an honor to present at this conference. Thank you very much for the kind invitation. So my name is, I hope you can see my screen. So my name is Deepak Jain. Right now, I'm an assistant professor at Optics and Photonics Center of IIT Delhi. It's a new center of IIT Delhi, which is completely dedicated to optics and photonics. We don't have any UZ program, but we are about to start a MTech Photonics program. And already PhD program is going on. So prior to this, I was at IIT Bombay. I'm also an optic ambassador, and my job is to promote optics and photonics, especially among the early career researchers, to help them out. And I'm also chair of the fiber bonding and fabrication technical group of Optica. Optica has around 40 plus such technical groups. And the job of this technical group is to organize different talks, events. So if you wish to know more about these groups, you can always contact me, and always feel free to contact me, because it's my job to help you out as an optic ambassador, especially for the young early career researcher, if they need any guidance. Thank you very much. So this talk is about next generation optical fibers for sources and communication. I've been working in optical fibers since my PhD time. So I did my PhD from Optoelectronics Center, University of Southampton, where I've been working over the different specialty fibers for light sources, such as lasers, for supercontinuum light sources. So I will talk about those sort of fibers which are required for lasing application. In part 2, I will talk about some different kind of optical fibers, and especially for the exploitation of nonlinearity to generate broadband supercontinuum light source. The difference between the conventional narrow line lights with narrow line width lasers is that they're monochromatic. On the contrary, supercontinuum light sources are fairly broadband, though coherent like as conventional lasers. In part third, I will talk about novel hollow core optical fibers. We know the fibers are the backbone of the telecommunication industry, but now hollow core fibers are emerging, which are supposed to be the future of the optical fiber technology. Then I will talk about single photon sources. There's a quantum budge everywhere, so I will explain what I'm doing with using these optical fibers for especially mid-IR single photon sources. Let's go to the part one. Fiber lasers are doing very well. They have good power scaling capability, good beam quality, different range of wavelengths are possible. Tunability is there, maintenance, footprint, ownership cost. So they are far better than other lasers for many applications. And if you see the market that is being captured by fiber lasers compared to other lasers, and the power levels are rising. So especially the decade starting from in the first decade of the century, fiber lasers have seen a dramatic progress. But now we know that life is not always good. So there are nonlinear effects such as cell phase modulation, stimulated Raman scattering, etc., which doesn't let the power scaling capability beyond a level. So this is a very basic schematic of a fiber laser where there's a core and cladding, and the pump light is being launched into a cladding, and then lasing happens into the core, and core is doped with rare earth ions. Physics is a good friend, but physics is not always a good friend. And these nonlinear effects creates a trouble in scaling the power level. So one of the quick solution to fix this problem is to use a large mode area fibers, basically large core diameter fibers. So what happens if there's a large core diameter, then it can accommodate more amount of power. Basically, these nonlinear effects, Raman, cell phase modulation, etc., depend on the power density. So if the core is larger, this central core is larger, then it will accommodate more power. It will allow to accommodate more power before the thresholds of the nonlinear effect come into the picture. As you can see from this formula, the threshold is directly proportional to the effective area. Effective area is basically it tells how big is your mode profile. But the problem is that as we go to a large core diameter, it becomes multimoded. So that's the problem. So people have fabricated and proposed different design. For example, photonic crystal fiber, very famous, leakage channel fiber, all solid photonic bandgap fiber, chirally coupled core fibers. Their job is to allow a large core diameter fiber, maybe around 50, 60 microns, something like that, but to suppress the harder modes. So there are channels made up where harder modes can leak out, while fundamental mode remains in the core. So this way, one can have effectively single mode behavior. This effectively single mode behavior is very important for lasing application so that there is a good beam quality. But the challenge is that these fibers are difficult to fabricate. As you can see that there's no cylindrical symmetry. So they require stack and draw process, which is very difficult. So therefore, the cost of such fiber is fairly high. Other than that, there's a critical requirement of refractive index match of the core and cladding. The refractive index of core has to match to the refractive index of the cladding, but these are the active fibers for lasing applications. So the core has to be doped with rare earth ions such as ytterbium, erbium, thulium, etc., which are index raising elements. So therefore, it becomes very difficult because these has to be simultaneously doped with the fluorine so that the refractive index of core can be same as of the cladding. So which makes the fabrication very difficult. So before I go into the detail of my work, what I did, so it's very important to define some criteria. Basically, there is a plethora of publication on this subject, but no one has tried to establish some standards. So here I talk about effective single mode operation, which is basically three things are important. What is the criteria? How do you define a large core diameter fiber to be having a single mode operation? So you need to define some criteria of harder mode suppression while keeping the fundamental mode loss to be lower than a particular level. So this discrimination is very, very important. So the criteria, okay, and the band radius, while the fiber will be coiled because to have a compact device size. So what is the band radius? while one is claiming, okay, I can achieve this much effective area of the fundamental mode, and that is good, but what is the suppression level of the high order mode and what is the band radius? So these things are very, very important. Higher is the criteria, it is better. Lower is the band radius, it is better because it would be compact device size, and effective area has to be higher. And other than that, it would be good if it is all solid design, then it would be easy to splice, easy to cleave. And if it is a cylindrical symmetrical structure, then it would be easy to fabricate, low cost fabrication. So now let's go to the next slide. So just I would like to give a brief introduction about the modified chemical vapor deposition process, which is a standard process for fiber fabrication. You will be hearing from Dr. Dhar tomorrow. He's a more expert of the CVD process. So here what happens, like all these precursors like germanium tetrachloride, silicon tetrachloride, they all come through the vapor phase into this tube, where the deposition of cladding and core happens, and thermophoresis is the process which is used here. They get oxidized, silicon tetrachloride get oxidized to silicon dioxide. So glass is largely made up of silicon dioxide. Different dopants can be doped here. This germanium tetrachloride can be oxidized to germania, which is germanium dioxide. So this is a standard process which is being used for specialty multi-core specialty optical fibers. VAD and OVD are other processes which are used for basically telecom fibers. And once a preform has been drawn, preform has been fabricated using this MCVD process that is drawn through this draw tower, which is mass in, mass out process. Basically, you can see this preform is usually 10 to 12 millimeter in diameter, and the furnace is used here to heat this preform, and which falls because of the gravity. And then there are the pullers, and then the fiber goes through UV chamber, basically, and polymer coating. So polymer is applied over the fiber, and then it passes through the UV chamber to polymerize the polymer. So that's the standard way of fiber drawing. Recently, another process of stack and draw has emerged, especially for photonic crystal fiber. Those who don't have this cylindrical symmetry here, the different capillaries are stacked together, and then it is drawn. So this gives additional flexibility to the fiber. This is no longer dependent on the CVD process, but this is a fairly complex process. Okay, so now, yeah. Other process, which is known as a solution doping process for rare earth doping of these active fibers, if you want to use them for lasing application, for an example, ytterbium dot fiber, erbium dot fiber, thulium dot fiber. So solution doping process, in that case, we don't deposit the core glass, we just deposit the shoot, we take it out over the lathe machine, and we top it with a rare earth solution. Rare earth solution may have ytterbium chloride, or thulium chloride, or erbium chloride. The suit of glass basically soaks the solution. It is usually for an hour. Then it goes back to the lathe machine where it gets oxidized over a low temperature from thulium chloride to thulium oxide, erbium chloride to erbium oxide, and ytterbium chloride to ytterbium oxide. So afterwards, preform is generally collapsed. So this is a very brief introduction how fiber fab works. So one of the objective of this work was to develop easy to fabricate simple fiber design, so the cost is low, very high suppression of the hardware modes, all solid fiber design, and compact device size, so that basically the band diameter is not larger than 40 centimeter, and the effective area should be somewhere in the range of 1000 to 1500 micron square. So such fiber should be good for kilowatt kind of output power level in continuous regime, and few hundreds of kilowatt pulses in the pulse regime. So before I thought of developing any specialty fiber, I thought let's have a look at the step index fiber. You must be all knowing the step index fiber. Cladding is there, core is there. So very standard step index fiber, which has a outermost low index polymer coating to make it suitable for the pump cladding. So we know that a very standard equation V number, which says in order for this fiber, this core to be single moded, this V number has to be lower than 2.405. So if we want a large core, A has to be large, then this Na term, Na2 square minus N1 square root has to be lower, right? So before my work started, researchers from Coherent already published this one, where they managed to achieve a 3 kilowatt output power. You can see here. Afterwards, a Raman effect started. They managed to achieve 0.048 Na, which is quite low, given it was a ytterbium doped fiber. So what we did is, like, we thought, okay, let's reduce it further. And we developed a lower NA, which was 0.038. So here the delta N difference between core and cladding is 5 into 10 raised to power minus 4. So basically, this surpassed the result in terms of low NA by coherent, and we could manage with this kind of delta N 5 into 10 raised to power minus 4, leading to delta N of leading to NA of 0.038, while coherent was close to 8 into 10 raised to power minus 4 with NA to be 0.048. We managed to have an effective area of 700 microns square, where the fundamental mode was having loss 0.1 dB per meter and the harder mode 10 dB per meter. So one could say, okay, what did you achieve by lowering the delta N slightly? We did achieve a great thing in terms of the effective area. So here the core diameter was 35 micron and the required band diameter was 32 centimeter, which is fairly okay in terms of the device size. So this is the performance of the fiber. Basically, you see we managed to get around 81% slope efficiency with respect to 975 pumping. So this is output power, this is absorbed power, and this is the lasing around 1040, basically 1040 nanometer. So good beam quality. And we also tested fiber by launching different harder modes like LP11 to see how it looks like. So we could see it's a mixed mode basically with the dominant LP11 mode. At the output, we could see it's just the LP01 mode. It has a huge suppression for LP11. We also launched the mode with offset access to make sure that it doesn't excite harder modes, which ensures that the fiber offered a very high losses to the LP11 mode, which is in a good agreement with theoretical calculations. As you can see here, this is LP11 losses, and this is just the LP01 loss. And at the 32 centimeter band diameter, the fundamental mode loss to be lower than 0.1 and harder to be larger than 10 dB. After our work, several other groups like Fraunhofer Germany and Coherent also tried different ways to fabricate ultra low NA, but you can see they had many problems like ripples were there in the refractive index profile, which is not good. In order to further scale the effective area, I propose single trench fiber. So here it's like a step index fiber only, but with a surrounding ring, something like this. So I call it single trench because there's a trench here, and it is a cylindrical symmetrical fiber, all solid fiber, and of course low index contrast, because in the previous work we already achieved how to achieve a delta N to be around 5 in 10 to the power minus 4. This work was very well accepted by the Clio and it was upgraded to an invited talk. So afterwards, like I sort of fabricating this, and but before I go into the fabrication, I would just explain how it works. A step index fiber basically is if you bend it, the effective equivalent band index profile becomes like this. So because of the bend, there will be coupling of the modes to the cladding. So you can see that this is unbent case, it guides 4-5 modes, but once you bend it, the harder modes gets coupled. You can see they are becoming lossy while the fundamental is still reasonable. But that loss discrimination is not high enough. But if you introduce this resonant ring, what it does basically, that there's a good coupling between these harder modes and these resonant rings. As you can see here, there's a very good coupling, and the harder modes see the significantly high loss. For example, here more than 5 dB, 50 dB, 140 dB, while the fundamental is still reasonable. So this way, by tuning the parameters of this ring, thickness and the distance from the core and the delta N, one can have a very high losses for the harder mode. So we did lots of numerical simulations to optimize this, and we could find that this criteria of 10 dB per meter for harder mode and lower than 0.1 dB for fundamental mode can be fulfilled at a band radius of around 20 centimeter while achieving an effective area of 850 micron square to 1120 micron square for different set of parameters. So this was indeed a good result. We first fabricated the fiber, and we produced a good reproducibility, like we repeated the process. And when we tested it, we again achieved around 75% slope efficiency with respect to 9.7 pumping, and you can see the lasing happening at 1040 nanometer. So in order to test it in a MOPA configuration, the fiber sample was given to another group where they tested it, and where they could find like 160 kilowatt peak power could be achieved with a slope efficiency of around 76% for this pulses of around 34 picosecond. So this is the amplified pulse, and this is the spectrum optical spectrum measurement of the output. So you can see the pulse around 1040. SRS started coming after 160 kilowatt, which is a significant result because for a 30 micron step index maximum you can go is 107 kilowatt. So in that way, it was significantly good. So similarly, we use the same technology for 1550. So here we fabricated another fiber where we used erbium in place of ytterbium. So ytterbium, erbium, lanthanum, and aluminum. Lanthanum and aluminum were doped to make sure erbium has a good solubility. We could manage lasing in this C band 1550 to 1560 with a very high slope efficiency around 46.3. This was a record result at the time. Also, I spent a lot of time in developing thulium doped fibers for lasers. So in thulium, basically, a very high amount of thulium dopants are required to achieve a slope efficiency. There's a phenomena 2-1 cross relaxation, basically. So pumping in thulium fibers is at 793 nanometer, which leads to lasing at 2 micron. So if there are enough amount of thulium ions, then it is possible to exploit this 2-4-1 cross relaxation, which basically basically you can say like if you make a one pump at 793 nanometer, you have one photon at 793 nanometer for pumping, then you get 2 photons at 2 micron wavelength. So we were the first to achieve around 70% slope efficiency at a time. So if I just compare different large mode area designs, this is a bit old work, around 2014, around 9-year-old work. So our work was like around 1000, reduced 1000 to 1500 effective area compared to other designs at a time. And I think it still holds. There's no reason for it not to hold. It was all solid design, cylindrical, symmetrical. Core index was higher than the cladding. So idea was that if you don't need a very dramatically high power, if you need a coilable fiber, so this work should be enough to meet the demand. During the same time, Professor Limpert's group at Vienna proposed the rod type fibers for more area scaling. They managed to achieve an effective area of 10,000 microns square, which is around is larger than by a factor of 10 what we achieved. Actually, the idea here is to keep fiber straight, don't bend it. So in our case, we bend the fiber length can be fairly long, 5 to 10 meter. Here, the fiber length is just around 1 meter maximum. So this was one good approach, but obviously the the device size was large and the fiber length was limited. And it suffers from model instability because thermal heat management is a big challenge. And of course, once the large pitch fiber was proposed and other fiber came, obviously other researchers were also working on the same problem. So we thought of also proposing something like that. So Bragg fibers were already there, they were published or possibly proposed by Professor Amnon Yariv in 1978. The first paper was published, I think, along that line. So this is a Bragg fiber. You see here is a core and high index rings surrounding the core. So basically there's a Fresnel reflection from these high index rings. So light can be guided in the core at certain wavelengths, and certain wavelengths, these ring modes will be in resonance and the light will go away into the cladding. Light will not be reflected back. So this is the refractive index profile of a fabricated Bragg fiber, which I did myself. And then I proposed multi-trench fiber. So multi-trench fiber, you can see, is an inverse of this Bragg fiber. This is a core and then low index rings surrounding the core. So this is a 2D schematic here. That is a refractive index profile. And this is the first ever multi-trench fiber fabricated by myself. There's a core and the ring you can see. Of course, it's not ideal, but this was the first attempt. It could be easily fabricated by MCVD process. This is all solid structure. So how it works, basically, it's interesting to see how multi-trench fiber works. So basically you see a core and cladding. Since there's only very limited low index, so there will be heavy coupling from core to the cladding. So you can see LP01 and LP11 mode, both are very lossy here. But if you introduce these resonant rings, it might be possible, depending on the thickness of these resonant rings, that only higher order modes gets coupled while the fundamental mode remain in the core. So LP01, the losses are low, but for LP11, it's high. So you can see by optimizing this again thicknesses of these resonant rings and all that, it is possible that to keep the fundamental mode to be fairly low while the higher order modes are to be higher. So we thought of like fabricating it and testing it. So first we fabricated, and numerical simulation shows that in rod type configuration, here this multi-trench fiber are for rod type configuration largely. So we could achieve around 12,000 micron square effective area, and we could also see If we just bend the fiber, around 1000 micron square could be achieved, which is due to the band-induced distortion. So this is the fabricated fiber. We tested it in, we could manage, to start with, we use a 30 micron fiber. These are the launched input beam. You can see heavily multi-moded beams were launched into the fiber, and then we could manage a very circular, nearly LP01 mode profiles. We also fabricated a 90 micron rod type fiber, though we didn't hit the right parameters, but this was also performing well. The fundamental mode losses to be lower than 0.05 dB, LP1 to be larger than 12 dB. Now, if I talk about what we are doing in this area, this is the work of the present 2023. So still, rod type fibers have done a great job, no doubt. They have produced the splendid results, but still we need a fiber which can be coiled and can offer a very large core diameter. So we have been working on this band compensated arc optical fiber. This was first proposed by John Finney at OFS Labs. They have a patent over the design. So basically idea here is to use a parabolic core and then a tilted cladding, something like that. So that if you coil this fiber, the equivalent design becomes something like this. We call it arc fiber because it's something like an arc for us, especially when the delta N core and delta N clad are fairly low. So we use this design and we did extensive study of different parameters for these delta N core and delta N clad. And we found something like this, basically fairly, if we optimize it like for different delta N core and different delta N clad, we found that we can achieve an effective area of more than 1000 to 2000 square at a reasonable coil diameter of around 30 centimeter. And you can see here the suppression of the higher mode was significantly high, and it can be even larger than 100 dB, while the fundamental mode can be lower than 0.01 dB. So the suppression can be on the 10 to power 4, basically 10 to power 4, which is significantly higher than the previous generation of the optical fibers. So, but yes, this was what we did. Like, I can't show a lot of results because we are optimizing at the moment and also in the process of publishing, but we managed to achieve 2500 micron square and 5000 micron square at 1060 nanometer wavelength. And the fundamental, and here the band diameter is lower than 1 meter. So, and fundamental mode loss to be lower than 0.1 dB while offering a loss of nearly 80 dB and 40 dB to the higher modes for 2500 micron square and the 5000 micron square respectively. Also, if we talk in terms of power delocalization discrimination, where how much the fundamental has power in the core and how much the other adder mode with respect to their overall power, we could see a significant discrimination, which ensures basically very good quality of fundamental mode can be preserved effectively while offering very high losses to the hard mode, even for these kind of effective areas. So the future is band compensated arc optical fiber for coilable fiber. That would be my conclusion. Now I will move to the part 2, where I will talk about mid-infrared supercontinuum sources. This is some work which I did at Technical University of Denmark as a Marie Curie Fellow as a part of my postdoc from 2015 to 18. So here the idea was to use, basically we know silica is the backbone of optical fibers, but silica doesn't guide after 2.4 micron, let's say, because it's a high phonon energy glass, and which limits the performance of silica. So silica is mostly for visible and near IR. So while there are other materials like germania doped silica, germania is a low phonon energy glass compared to silica. It can guide up to 3 micron. Giblan can guide up to 4.5, telluride 5 micron, indium fluoride 5.5, chalcogenides. There are different chalcogenides like arsenic sulfide, arsenic selenide, germanium arsenic selenide, telluride, etc. They can guide up to 20 micron. One might say why there's so much interest in mid-IR region 2 to 3 or even beyond that, because there are several gases and molecules which have their fundamental vibrational absorption band around, for example, for CO2, 2 and 2.7 micron, ammonia 2.3 to 2.9, CO2 2.3. So if we can make photonic devices in this band wavelength region 2 to 3 micron or even beyond, that would be good. So people have been already exploring germania doped silica fibers for several applications before my work, especially especially by the Russians, basically at the Fort Fiber Optic Research Center. So they managed to develop basically around very high doping of the germania in the core. So basically you can see it's a silica fiber only, with the cladding is made up of silica, but core is made up of germanium, 70 to 80% germanium. Even in some of the fibers, they claim to be 100%. And then they use this fiber for supercontinuum generation. Supercontinuum generation happens where you launch a pulse, a very intense pulse at a fixed wavelength around, especially zero dispersion wavelength, and then you let it broaden because of the different processes, solid off fission, etc. I won't go into the detail. So these were the results. Those were produced before my work. You can see here, they managed to get some broadening up to 3 micron, basically. Good light source, but you can see there were ripples, there were absorption band, asymmetry. So there were many issues. So and after this, I did a collaboration with Nanyang Technological University. At the time, they had significant facility, MCVD machine there. So they fabricated this fiber. You can see a very high refractive index difference between core and cladding here. So this was around 74 mole percent germania in this. And this is a fiber transmission out of a very small piece of fiber. You can see, guys, more than 3 micron. And this is the dispersion we managed. And you can see from here, zero dispersion of the fiber to be around 1.6, which is much larger than germania fiber, silica fiber. So I tested this fiber for the supercontinuum generation by using a MOPA. I built a MOPA in-house. MOPA was at 1550 because the zero dispersion around 1.6 micron. This was a few stage MOPA, and you can see a very sharp peak at 1550 at low wavelengths. But as soon as I got more and more power, the pulse was brought up dramatically high. And it was indeed required because we wanted to go as long as we can go. And this is known as in-amplifier supercontinuum generation, basically. So first I used this highly germanium doped fiber around, which was having around 3.5 micron core diameter, 22-meter long piece of fiber. And I could manage up to a supercontinuum generation up to 2.6 micron. Then I reduced the length. I could manage up to 5 meter. Then I use a length of around 1 meter, 0.9 meter. I could manage up to 3 micron. You can see very broad source, no OH dip, which was there in the previous work. So this shows that the fiber was lossy, obviously above 3 micron. So optimum length is fine enough to obtain a fairly broad source. So this was at the time a record result. Of course, many researchers have produced better result afterwards. So we managed to get around 1.44 watt output power, which is of course limited by the pump power from 700 nanometer to 200 nanometer. Afterwards, I managed to get another piece of fiber from my colleagues at NTU Singapore. This was 70 mole percent germania and 9 micron core diameter, which allowed to launch more and more power. So this is the outcome. You can see with using around a 1 meter fiber, we managed to get up to 3 micron. So 20 dB bandwidth was from 1 micron to 3 micron. Output power was significantly high, around 6 watt. And afterwards, in order to further scale and this long wavelength edge, what we did basically out of this MOPA, we use a thulium dot fiber, and we launched the power in output power in this germanium dot fiber. These were the new fiber, batch of new fiber, and we managed to get up to 3.4. And you can see fairly smooth profile here. There was just some OH dip, obviously because of the OH. So even at a very low power, very low input current, around 16 milliwatt, we could manage to have a fairly broad spectrum. So the results were published in JOSAB in 2019, around 4 years back from now. So the 10 dB and 20 dB edges were at 3200 nanometer and 3300 nanometer. This at the time, this was basically one of the best results in the germania case. I also spent building the GBLAN-based supercontinuum sources because, as I said, GBLAN can guide up to 4.5 micron. Here, the GBLAN, you can see these were some of the results which I obtained, and you can see fairly flat supercontinuum generation, which goes up to 4.5. Idea was to push more and more light beyond 3 micron. We wanted to make an OCT system, optical coherence tomography system. We want to use this laser source at 4 micron. So we managed to get 100 to 200 milliwatt output power beyond 3.5 micron, where the overall output power was around 1 watt. So this GBLAN supercontinuum source was used in mid-IR system, the first world mid-IR system at 4 micron. This was published in Nature Light Science. So this is a source I built. And later on, this has been commercialized, and company known as Norbliss, Nordic Broadband Light Sources, is running already. And now not just the PCT application, few patents are also there. So I also learned some entrepreneurship there. And afterwards, I moved to University of Sydney from 2018 to 2021. So where I invented a design fiber design, which can do the beam shaping basically. So I call that beam shaping optical fiber. So you must be using these laser pointers where you see a laser beam on the cross-sectional profile of the laser beam on a wall or on a screen. You can see it has a highest intensity in the center, which gradually fades away basically, which is okay for the presentations. But for many applications, we need customized laser beams, basically maybe elliptical, maybe flat top beam. But there are many applications. For example, just to give you more illustrative example. So this is a conventional beam, Gaussian beam. Because of the Maxwell's equations, they acquire the Gaussian beam. But there are many applications which require such beam, flat top beam, annular beam. So the current state of the art optics is available from different companies to convert these beams, but they are bulky, they are not integratable with the fiber, expensive, and some of them cannot handle the high power. This is another issue with the, you can see with this laser diodes, which emits elliptical beam, okay? And we normally use a fiber coupled laser diode, but in order to couple this elliptical beam to the fiber, there's some special optics is required. So if we can develop some fibers which can convert the beam inside it. For example, this is a laser diode, this is fiber, we are just coupling, we are coupling or connecting this using this sleeve. So elliptical beam is launched and this elliptical beam is being converted to the Gaussian beam. So if we can do that, that would be great. That was a motivation behind this work. So basically, I thought of developing this design. I cannot show the design, unfortunately, because it's under patent and it's being commercialized. So here the idea is that if you launch an input beam, for example, a Gaussian beam, you can get flat top beam, annular beam, or a triangular beam, and not just the passive ones. It can be designed in such a way that it can be active. So they are fairly cheap. The cost we have figured out is like $500 per meter. They can handle very high power, very low loss coupling efficiency. Uh, Conversion efficiency is nearly 100%, large bandwidth. So there's a huge industrial potential. Therefore, our company Spec Photonics has already been started in Adelaide. Innovise, a firm, showed an interest at uni to convert this work into a commercial entity, which is very good. So soon the fibers will be available in the market and people will be able to use it. Now I will move quickly to the part 3, where I will talk about novel hollow core optical fibers. So we all know light travels in a solid core fiber in a high index medium because of the total internal reflection is the basis of these solid core fibers, or which our communication relies, the internet relies. But how about if, let's say, we can design some fiber where light travels in the air? That would be great, because in that case, there will be no material loss, there will be no material dispersion, there will be no non-linearity, because this solid core fiber produces the linearity. And there will be no reduced speed, because if light travels in a medium or a glass with a refractive index n, speed gets reduced by c by n. So if light can travel in hollow core fiber, that would be great. By hollow core, I mean the core is made up of air only, and the cladding has some material. But how it is possible? Because we know total internal refraction requires the core to be having higher refractive index than the cladding. But this is possible. Here, total internal refraction doesn't work. People have been working from last 2 decades. So you can see some of the design. This picture has been taken from Professor Polithi's paper published in Optics Express. So early designs were based on photonic bandgap concept. They were fairly complex to fabricate and the losses were higher. And I would say it was in 2014 when this design came into the picture by Andrei Priamikov at Fiber Optics Center, Russia, which they call sort of revolver fiber, and it works on anti-resonance. And so this negative curvature is very, very important to have the law loss. So what happens when the light is there? It tries to move in this and in this other directions, but because of the anti-resonance, it gets spectraflected. And when there will be resonance, it will be coupled to the cladding. So resonance and anti-resonance. So these designs are doing a great job, especially this NANF from Professor Polithi's group, and which has, I think, now been commercialized as well. So they started a company, Luminosity, and which has been now bought by Microsoft as well. So here you can see there are 2 nested elements, and there's a nodeless. There's a no node. These tubes are not connected. So light can be guided into this core by reflected by these rings, and the losses can be as low as you can see here. So this is a picture shared by Dr. Thomas Bradley on LinkedIn. Here you can see this is the lowest possible loss from the solid core fiber, 0.142 dB per kilometer. And using this fiber of 26.2 micron diameter, the losses has gone down. obviously, these fiber have a high potential to have very, very low loss. So our idea is to work on developing couplers, connector, isolator, amplifiers, which are compatible with hollow core fiber. Because with the advancement in hollow core fibers, 1550 nanometer is no longer the lowest loss wavelength. So we are working over that. So recently, but before I go into our work, hollow core fiber have huge application in the data centers. In data center, information flow per unit area and latency is the key. So they have a huge market. The speed is very, very important. Latency is about the speed. Low latency is required so that there's a less delay while moving the data from one point to another point. So recently, Microsoft bought Elamassie, and they are the masters. And we have designed a new fiber. We call it DNCF, double negative curvature fiber. I cannot show the design because we are in the process of patenting, but our design offers lower losses than NANF. So this is still the preliminary results. We are working hard. So maybe in the next time I will be able to show you the design, but idea is same. So idea is same that it's a anti-resonance and you have to optimize the design in such a way that you get the low losses. Okay, now I will move to the part 4, novel optical fibers for mid-infrared single photon sources. We all know there's a buzz about quantum and people are talking about quantum computers, quantum imaging, quantum sensing, quantum communication. So why single photon sources? Basically, when you have any conventional or classical photon source, you will have the bunch of photons, okay? But when there's a single photon source, means you have one photon at a time. So it becomes easy to deal with that, and it basically gives you more security. For example, if you don't know how many photons are coming, if someone can steal some of the photons, information will go there. But if you know only one photon is coming at a time, another will follow by the difference of this much time, then it would be hard to steal those photons. Right? If those would be stolen, then you would learn, okay, yes, photon has been stolen. So basically security can be done and they weakly interact with the environment over the distance, which results in lower noise, loss, etc. And they can be manipulated with the linear optics. So single photon sources have become backbone of the quantum information. And there are, of course, a number of ways to produce a single photon sources. But since I'm a fiber person, so I would like to develop the single photon sources in fibers. And already people have demonstrated fiber-based near IR, near infrared single photon sources around 1550 and at other wavelengths. So here you can see, but one might ask, why do you need a fiber-based single photon source? Because again, the advantage of the perturbations it can withstand, basically, the generation can take place within the fiber and fiber can deliver the single photon. They don't require the realignment. They are not sensitive to vibrations and temperature like these sources where elsewhere the photon generation is taking place and then it is being coupled to the fiber. Here, this is the diamond nitrogen vacancy center, very famous, and fiber is here, so it is being coupled to the fiber. Similarly, here and it's a quantum dot. So there are a number of ways, but my preference would be fiber. So we have been working rigorously to develop mid-IR single photon sources. Not many people are working over mid-IR single photon sources. There's not even a single source, especially on fiber, and there are very few papers on other ways of developing. So for single photon source generation, we are using four-wave mixing. We are producing the phase matching conditions. So right now I am exploiting Germania core fibers with silica cladding, which are the potential candidates here in 2 to 3 micron window. By optimizing the core and Na, it is possible to obtain the zero dispersion or phase matching condition at different wavelengths. So this is being formed at 2 micron. Here we have achieved the phase matching condition for a wide range of frequency shift. Obviously, again, this work is under process and some part is under patenting, so I can't talk a lot about that. So basically, we are exploring mid-infrared single photon sources by employing different optical fibers using different materials. We are also looking forward for giblan and chalcogenide fibers. Of course, that will be more tough, but that's our long-term goal. Thank you very much, and I think I'm done, and I hope I finished on the time. Thank you. I'm happy to take questions if there are any questions.
Thank you very much for a nice presentation. If you have any questions, you are kindly welcomed. I guess there is no question. Thank you very much again.
Thank you. Thank you. It was a pleasure and good luck with the conference. Thank you. Take care. Bye.
Hello again. Now it's my pleasure to introduce Professor Santos Kumar, PhD from IIT-TAM and currently professor at Liaocheng University, China. Recognized among the world's top 2% scientists, Dr. Kumar's impactful research includes more than 310 articles, 2 books, and a recent patent application for groundbreaking optical fiber sensing technology. As a fellow of SPIE, life fellow member of OSI and senior member of IEEE, Optica and SPIE, Dr. Kumar holds leadership roles. Today, he will discuss plasmon-assisted inline optical fiber sensors towards healthcare applications. Please join me in welcoming Professor Santos Kumar. The stage is yours.
Yeah, thank you. Thank you so much for the nice introduction. And also thanks for the invitation to give the talk.
Yes, we can see your presentation right now.
Yeah, so thank you once again to committee member to invite me to give a talk on the plasmon assisted inline optical fiber sensor for the healthcare application. So myself, Santos Kumar, currently working as a professor in Liaocheng University, China, and also working as a associate editor of IEEE Sensor Journal, IEEE Internet of Things, and Biomedical Optics Express, and also working as a chair of Optical Biosensor Optica Technical Group and Optica Traveling Lecturer. So in this case,
sorry, we are only seeing the desktop. Okay, now we can see the presentation. Please continue.
Yeah, thank you. So this is our Liaocheng University is situated in a very beautiful city, that is the Liaocheng city, and there are so many lakes in this city, and so this is also called as a lake city. So these are the few snaps of our lab, a biosensor lab. We have a very good instrumentation facility for the optical fiber sensor fabrication and as well as the biosensing applications. So in this presentation, mainly I will discuss about the optical fiber sensor, those advantages, applications, and I will also discuss about the most significant and important phenomena, that is the surface plasmon resonance and localized surface plasmon resonance phenomena. And based on this phenomena, we have developed several kind of the optical fiber sensor for the detection of several biomolecules like alanine aminotransferase, histamine, acetylcholine, creatinine, cardiac troponin, cholesterol, glucose, dopamine, uric acid, ascorbic acid. So these are the biomolecules found in the human body. And so I will discuss why this work is important. And as well as we have also developed several sensor for the microorganism detection, like cancer cell detection and bacteria detection. So in this presentation, I will discuss the few of the work due to the time limitations. So first of all, we will know why this work is important, especially for the healthcare application. So these are the few data of World Health Organization, WHO, that due to the cholesterol, around 0.6 million deaths occur each year, and due to the liver injury, around 2 million deaths occur every year. So similarly, around 10 million deaths occur due to the cancer, and diarrhea. This is very prominent in the children, and around 0.6 million deaths occur each year. So we tried to develop a sensor that is the portable, scalable, and affordable early diagnosis technique so that we can diagnose the uh, these concentration earlier, and we can go for the treatment. So in this way, we will try to reduce the number of deaths. So for this purpose, we would like to develop the healthcare optical biosensor. So first of all, we will try to understand what is the optical biosensor. So in this we can see there are three main part. The first part is the sample, then biorecognition element, and the optical transducer. So sample means glucose, cholesterol. These are the different kind of the samples that is found in the human body, or we can say the blood or serum. So if we would like to detect those things, we need some particular biorecognition element, that is the a specific enzyme or antibody or protein, nucleic acid receptor, etc. So when just like we can take an example of the glucose. So when the glucose and the glucose oxidase enzyme will react, then at that place there will be some changes occur. Okay, so that changes like it produce the gluconic acid and H2O2. So due to change in the H2O2, it will change the refractive index of the surface. So that change can be sensed by the different kind of optical transducer. So there are several kind of optical transducer, that is SPR, LSPR, interferometers, resonators, gratings, refractometers. Okay. So with the help of this optical transducer, we can identify the changes and we can get in the form of the signal in our computer. So that's why the optical biosensor detects a chemical or biochemical substance by transducing a biological interaction into electronic or optical signals. So that is very effective for the biomolecules detections, bacteria detection, virus detection, toxin, drug, antibody, and tumor cells. So here we will try to understand the importance of the optical fiber sensor in our day-to-day applications. So here we can see the optical fiber sensor can be developed with the help of different kind of the optical fiber, that is single mode fiber, multi-mode fiber, hollow core fiber, plastic optical fiber, multi-core fiber, and photonic crystal fiber. Okay, so with the combination of these, or with the help of these optical fiber, we can develop a different kind of the sensor for the specific three major applications. The first application is chemical detection, like need detect the heavy metal ions, gas concentration, chemical reagents, and pH detection. So similarly, in the vector quantity detection, like magnetic field detection, temperature, humidity, and curvature. The most important is which we target, that is the healthcare application for the biomolecular detection. So for that purpose, like protein detection, cancer cell detections, amino acids that found in the human body, and bacteria. So overall, we can see we can uh, these sensors are very important. Even in the we can use this sensor in our home, to detect the humidity, temperature, gas concentration, water quality, and some bacteria growth, and these things, so that we can keep our family happy. Okay, so there are a lot of application of the optical fiber sensor. So in this presentation, mainly I will focus on the biological detection or biosensing. Okay, so next question is, what are the advantages of optical fiber based biosensor? Okay, so first advantage is the biocompatibility. This is very important because uh, the optical fiber is made up of the silica, and this optical fiber can be used in our human body, or we can also use in the serum, or we can say the biofluid, and it will not react. So this is the biocompatibility, and that is very important for the biosensing purpose and especially for the health monitoring applications. Okay. Second is its reduced size, flexibility, and low weight. So due to this advantage, sometimes we can also do the diagnosis of some of the disease inside the human body without the surgery. We can insert the optical fiber and we can do the diagnosis. So due to the flexibility and reduced size in nature. Okay. So third is the low cost, and next is the capability to work in hazardous media. So optical fiber we can use in the nuclear environment or under the sea, at the any place we can use it. Okay. Next advantage is very important, and we will try to understand the electromagnetic interference immunity. So what happened in microwave communication or microwave, the wavelength is in the range of the centimeter. Okay, so this electromagnetic interference will happen when the distance between the wire will be the comparable to the wavelength. So it is chances of the electromagnetic interference in the microwave, but in the optical communication, due to the higher bandwidth or higher frequency, the wavelength is in the range of micrometer. So it is very difficult to get the micrometer distance between the two fiber. Okay. So due to this, there is a very less chances of electromagnetic interference in optical fiber as well as optical fiber sensors. Okay. So next is a very important, and that is very popular nowadays. People are trying to develop or use the sensor that can detect the multi-parameter. So that several like a temperature, pressure, strain, or even in the case of the biological detections, people would like to use the sensor that can be useful for the multi-parameter sensing. Next is the diversity of light propagation configuration. So in optical fiber, we can mold the light flux as per our need, and we can develop the sensor as per our application or as per our need. So these are the so many advantages of optical fiber sensor that is very good than the conventional sensor. Okay. So next is the phenomena. There are a lot of the sensing principle, optical sensing principle, but here my talk will be mainly focus on the plasmonics. So the plasmonics is nothing but a coherent oscillation of electrons at metal dielectric interference. So based on the coating or based on the thickness, there are two kind of the plasmonic behavior. The first one is the thin film based, that is also called as propagating surface plasmons, and second one is the nanoparticle based, that is the localized surface plasmons. So what is the propagating surface plasmons? So it is nothing but the collective oscillation of conduction electron at metal dielectric interface under the influence of incident electromagnetic radiation. So we can see due to the metal dielectric interface and incident electromagnetic radiation, the electric field is introduced at the surface of metal and dielectric. Okay. But in the case of the nanoparticle, we can see the density oscillation of conduction electrons inside metallic nanoparticle under the influence of incident electromagnetic radiations. So that electric field introduced at the surrounding of the nanoparticles, and this electric field intensity is very sensitive to the any external changes, and that will work as a sensor. So our work will be mainly focused on the nanoparticle based sensor. So still there is a two very important phenomena, the surface plasmon resonance and localized surface plasmon resonance. So we will try to understand the both phenomena. So here we can see This is the common conventional optical fiber. So in that there is a core, and this is the cladding. And as we know, we send the light in the core. So with the help of the total internal reflection, it travel inside the core. Okay. So if we would like to make it a sensor, then we try to remove the cladding from the surface. So there are several methods of the remove the cladding. So mainly the popular method is the using the HF acid, hydrofluoric acid. We can remove the cladding and the thickness as per our application. So, okay. So what is the purpose to remove this cladding? So we would like to get more and more evanescent wave at the sensing area. Okay, so we, after removing the cladding, we do the coating of the thin film. So thin metal film, normally the gold, silver, copper, and aluminum. So in that, mainly the gold and silver is more popular for the SPR phenomena. So what will happen? So when we will launch the light, so due to there is a evanescent wave, and due to the metal and dielectric interface, the one more kind of the wave will generate, that is the surface plasmon wave. Okay, so when the propagation constant of evanescent wave and surface plasmon wave will match, then a resonance will occur, and at that time a deep wavelength, or we can resonance wavelength, we can get. But what happened in localized surface plasmon resonance? In localized surface plasmon resonance, at the place of metal thin film, there is a need to do the coating of nanoparticles. Means the size of the particle will be less than 100 nanometer. So due to the nanoparticle, what will happen? So when we launch the light, then due to the incident frequency, the electron inside the particle will oscillate, and that will uh, produce the electric field intensity, electric field around the nanoparticle. And here we can see the each nanoparticle will be a very sensitive. So to make the biosensor, the biorecognition element is very important. Okay, so we, after coating of nanoparticles, we need to combine the biorecognition element. Okay, and when we, the analyte will combine with the biorecognition element, then there will be some changes will occur on the surrounding of the nanoparticle. Due to these changes, there will be change in the peak wavelength, and based on this peak wavelength or resonance wavelength, we can determine the concentration, as well as we can also determine the type of the biomolecules. I will discuss how we can also detect the type of the biomolecules. So our group has developed several novel fiber structures, such as this structure is made with the combination of single mode fiber, multi-mode fiber, and photonic photosensitive fiber, then again multi-mode fiber and single mode fiber. So this multi-mode fiber is working as a splitter, and provides the core mode into the higher modes, and provide the into the cladding mode, and we can get the more and more evanescent mode at the evanescent wave at the sensing area. And another multimode fiber working as a combiner, and again it will come into the single mode fiber. So this is just like a magenta interferometer. Okay, so similarly our group has also developed the tapered fiber structure, fiber ball structure. Fiber ball structure is very interesting. We can develop the ball at the one end of the fiber, and we can use this for the sensing purpose. We have also developed the multi-tapered structure. So in that there are several tapered structure in single fiber. Okay, so we have also used the photosensitive fiber, and we etched and expanded the core and used for the sensing purpose. Okay, so later on we have also used the multi-core fiber. This is the 7-core fiber, and we etched and expanded the core of the multi-core fiber for the better sensing applications. So here we can see the core is expanded with respect to the um, time, and here recently we have developed a new kind of the optical fiber sensor, that is the wave flex sensor. So this is mainly introduced by our lab, and in that we have developed not a single tapered fiber structure, the multiple tapered fiber structure, and the very novel kind of the sensing structure. So this is based on the, this is the optical fiber that is based on the uh, plasmonic wave phenomena. So this is the reason we called it as a wave flex sensor. Okay, so here this sensor is very important, that is the humanoid tapered structure. I will discuss this structure in next few slides. And this one is the tapered in tapered structure, and this one is the tapered in tapered with 4 tapered. So these are the very new structures developed in our lab. I will discuss in detail about the fabrication, how we have fabricated and used for the biosensing applications in the next few slides. The simple optical sensitive the biosensing purpose. Okay, so these are the few more sensing structures, novel sensing structures, combination of the different kind of the fibers, and further enhance the sensitivity or sensing performance, we use the different kind of the nanomaterials. Okay, so especially we use the gold nanoparticles and the silver nanoparticles for the sensing application, that is for the LSPR principle, and other nanomaterials or 2D materials like a graphene oxide and multi-walled carbon nanotube, okay, and copper oxide nanoflower, copper oxide nanoparticles, and molybdenum disulfide nanosheet, cerium oxide nanoparticles, molybdenum disulfide nanoparticles. We have used, as well as also used the MAXine and zinc oxide nanoparticle to improve the biocompatibility nature of the sensor. It what happened? It normally help to enhance the combination of or functionalization of enzyme or antibody on the sensing purpose, and it improves the biosensing performance. Okay, so we will see how we can fabricate and we develop this kind of the sensor. So for the fabrication, firstly we developed the new kind of the sensor structure, optical fiber sensor structure. Like this is the use the single mode fiber, and then we using the combiner manufacturing system machine, we have developed a very fine quality of tapered structure. Okay, and after the fabrication of the fiber structure, we have synthesized or characterization of the nanomaterials. So for the gold nanoparticles, we synthesize using the very popular turquoise method, and in that we need to use the chloroauric acid and trisodium citrate, and with the help of that we can develop the different diameter or desired diameter of the gold nanoparticles. Similarly, we can synthesize the uh, graphene oxide using the modified hammer method. Okay, so in that we can use the graphite powder, and with the help of the chemical procedures, we can synthesize the very good quality of graphene oxide. Okay, so in this way we have used or synthesized and used the several nanomaterials in our work. If someone is interested, they can refer our work. So after the synthesis of the nanoparticle, the most important task is to how we can immobilize the nanoparticles on the optical fiber. So for this, we need to follow the some of the chemical procedure. I will discuss the detailed process in a few slides. Okay. So after that, after the functionalization or immobilization of the nanomaterials, we verify the coating process, functionalization process with the help of a scanning electron microscope. Okay, so in that we can see these are the gold nanoparticle coating. This is the very fine quality of the coating on the optical fiber using our developed protocol or developed method. Okay, so in this way, this is the sensor structure. We have these pictures are taken from the ACM. Okay, see, then so here we have fabricated the fiber, then synthesized the nanoparticles, then we did the coating of nanoparticle on the fiber, and then we have also verified the functionalization. And after that, we need to do the functionalization of biorecognition element. If we would like to do the target of the biosensing, this is the very important. Okay, so in this process, we do the we follow the some of the chemical procedure. I will discuss this process in detail, and we can do the functionalization of enzyme or antibody in this process. Okay, so in this way our sensor will be developed, and after that we can do the characterization of sample or we detection of the sample with the experimental setup that is based on the tungsten hydrogen light source and the spectrometer, and this is our sensor structure, and that is coated with the different nanomaterials and the biorecognition element. And after detection we can also verify the other sensing performance like reusability, selectivity, reproducibility, stability, pH test. We do several tests before finalize the sensor structure. Okay, so this is the complete process of the fabrication and testing of the optical fiber sensor structure. So here we will try to see how it works. Okay. So this is the simple tapered fiber structure, and uh, in that we can see there are three important regions. The first region is the general region, and the second region is the transition region, and third most important region is the tapered waist region. Okay, so that tapered waist region is also called as the sensing region. Okay, so here we can see how it works. So here when we send the light from the core, then at the transition region the core mode is converted into the higher mode, and we get the more and more evanescent mode at the sensing area. Okay, so when we do the coating of the metal nanoparticles, then due to the this input frequency, it resonance happen and it oscillate like this, and this is very sensitive to the external change. Okay, so this is the main sensing principle to sensing work. Okay, so here based on this phenomena I want to discuss the few sensor structure. So first one is the tapered fiber structure based LSPR sensor for alanine amino transferase detection. So here we can see why this work is important. So as we know, the alanine amino transferase, or we also called as ALT, is a necessary liver enzyme and is a type of serum transferase whose activity must be determined in order to diagnose and estimate the liver disease. So when there will be a liver injury in our human body, so this kind of the enzyme secrete more, and if there will be a ALT enzyme concentration in our serum will be high, then it means there is a liver injury and we can go for the treatment. Okay, so these are mainly the diagnosis process. Okay, so here we can see the normal activity level of the ALT enzyme in the serum is between the 5 to 40 unit per liter. So if its concentration will be high, then there will be some liver injury. So here we tried to develop the sensor to detect the concentration of the ALT. So this sensor, or we can say the liver alanine aminotransferase sensor, is based on the tapered in tapered fiber. So everyone know about the taper fiber. So here we will try to understand what is the taper in taper fiber. So what happened? We use the conventional uh, single mode fiber, SMF fiber, that is the core diameter is 9 micrometer and the cladding diameter is 125 micrometer. So we using the combiner manufacturing system. This is a very fine quality of the tapered machine, in that there is a 3 electrode and that discharge in the presence of the partial vacuum, and with the help of the left and right clamp we stretch the with the help of the computer programming we stretch the fiber. Okay, so uh, so it can firstly we have tapered from 125 micrometer to 80 micrometer. Okay, and here we have tapered like 3 structure, and then we have also shown the scanned the diameter, and we found the diameter is very accurate of the all fabricated fiber structure. So we can say the repeatability is quite high of the this kind of the sensing structure. Okay, so later on then we find accurately uh, we find the center point or discharge point, and again we tapered at the fiber and for the 40 micrometer. Okay, so here we can see we have taken the diameter scan, and its diameter is it was 125, then it 80 micrometer, and then its diameter is 40 micrometer. So this is the region this fiber structure is tapered in taper structure. Okay, so this is the detailed description of the this fabrication machine, that is the based on the 3 electrode discharge technique, and we have several camera to visualize the um, tapping process and scan the diameter. Okay, so after that we synthesize the several nanoparticles like gold nanoparticles and molybdenum disulfide and cerium oxide nanoparticles in this work. So the gold nanoparticles is mainly helping in the LSPR, and the other nanoparticles increase the biocompatibility of the sensor probe. So as I already discussed, how we can synthesize this kind of the nanomaterials, and primary investigation or characterization we did through the UV visible spectrophotometer and by measure the absorbance spectrum. So like for the gold nanoparticles, if the absorbance spectrum is from 519 or 520 nanometer, so its diameter is around 10 nanometer. So further we can verify through the ACM process and HR high resolution transmission electron microscope. So in this way we can do the characterization of the other nanoparticles. Okay, so question is that how we can do the coating of this kind of the nanoparticle on the fiber structure. So for the coating process, firstly we need to clean the fiber structure. So for the cleaning purpose, we need to follow the 3-step cleaning process. In that, first we need to clean the fiber structure using the acetone acetone for the 20 minutes. Then we need to clean the fiber structure using the piranha solution. The piranha solution is the combination of sulfuric acid and H2O2 in the ratio of 7:3, and for the 30 minutes, and then we need to wash with the water. So this process the mainly produces the OH group over the fiber structure. Okay, so after cleaning process we need to use the MPTMS. MPTMS is the special kind of the reagent which work as adhesive for the gold nanoparticles, and we need to do the coating of MPTMS for 12 hours in ethanolic MPTMS solution that produces the SH group over the fiber structure. Okay, so after that we need to do the rinse the MPTMS coated fiber with the help of ethanol and nitrogen gas so that remove the MPTMS unbounded MPTMS solution, and then we use the deep coating method and dipped in the synthesized gold nanoparticle for the 48 hours so that the gold nanoparticle is attached to the SH group on the sensing structure. And after 48 hours, again we rinse the fiber with the ethanol and nitrogen gas so that if there is unbounded or cluster of the gold nanoparticle on the fiber structure, then that will be removed and we can get the identical or we can uniform layer over the sensor structure or fiber structure. So similarly, for the other nanoparticles, we need to follow some of the chemical procedure or annealing method, and we can do the coating of the MOS2 and cesium oxide nanoparticles on the sensing structures. So these are the nanoparticle immobilization process over the fiber structure. And after that, for the enzyme functionalization, we need to follow the specific chemical process. Like firstly, we need to do the coating of MUA on the metal coated sensor structures. So MUA produces the carboxylic group on the sensor structure, and after that we need to activate the carboxylic group with the combination of ADC and NHS. Okay, so after that we need to do the coating of the specific enzyme using the deep coating method, and in this way the functionalization of the enzyme will complete. Okay, so how this sensor can work. Okay, so here we can see after coating we have done the characterization of the fiber structure, and here we can see this is the sensing structure, and here we have done the characterization stepwise. So the first process is the coating of the gold nanoparticles. So we can see the gold nanoparticles are very uniformly coated on the fiber structure, and after that we have done the MOS2 over the gold nanoparticles. Then above that we have done the cerium oxide nanoparticles. So how we can say that this is the gold nanoparticle, this is the molybdenum disulfide, this is the cerium oxide nanoparticle. So for that purpose we did the ACM EDS, energy dispersive spectroscopy, and we can able to know the material composition of the coated fiber structure. Okay, so we did that process and we found the coated nanomaterials. So here we can see this is our experimental setup. This is the light source and a spectrometer, and this is the sensing structure. So this work is very important because in this we are not using the some biomolecules. We are using the ALT enzyme. We are detecting the enzyme itself. So what we did, firstly we did the external reaction of L-alanine and alpha ketoglutamate in the presence of ALT enzyme that produces the L-glutamate and this biomolecules. So after that, the L-glutamate we kept on the sensor structure, and as we know, the sensor structure was coated with the glutamate oxidase enzyme. So when the L-glutamate and glutamate oxidase enzyme react, then the changes occur, and that we can identify with the help of the our sensing structure. Okay, so we have used the different kind of the ALT enzyme, and we can see there are different peak wavelength obtained with the respect of the different kind of the ALT concentration. Okay, so this is the linear range that is from 0 unit per liter to 1000 unit per liter, that completely cover the normal range of the ALT enzyme in human body, as well as it also covered the higher concentration, much more higher concentration of ALT concentration. Okay, so how we can we have also done the sensing performance test, and here I have shown the one result, that is the selectivity test. So we have detected the glycine, ascorbic acid, acetone, glucose, other things using our developed sensor, and we found that our sensor is quite effective for the ALT enzyme, not for the other purpose, because this is the enzymatic sensor, and that mainly works with the ALT, not with the other sensors. So in this approach, we developed one more high quality of the sensor using the tapered in tapered, and if you can see that this is the tapered, then again tapered, and again this 1, 2, 3, and 4 tapered structure. Okay, so after that we have coated the some of the nanomaterials like gold nanoparticles and some new kind of the nanomaterials, and here this sensor is very effective than the earlier sensor, and its performance is quite better than the earlier. Okay, so here we can see that this ALT enzyme we use, then it produces the L-glutamate, and again L-glutamate we used on the sensor structure, and then we got the NH3 and H2O2. So this H2O2 is very common, and if you are able to see the biomolecules work or some biosensing work, so in the most of the cases the H2O2 produces, and with the help of this we can determine the concentration of the or develop the biosensor. Okay, okay. So here we can see we have in this work we have developed the tapered structure, then taper in taper structure, and this is the new kind of the structure, and that is the TIT4T. Okay, so we compared these three structures, and we found that the TIT4 structure is quite better than the other sensing structures. So this is the process of the fabrication. Firstly, we kept 40-80 micrometer, and then the 4 different kind of the 40 micrometer. So this is quite difficult because the distance between the one tapered is only 1000 micrometer. So it is quite challenging, but our group developed this kind of the sensor, and in this work we have used the graphene oxide and multi-walled carbon nanotube, and here that I was talking. So here we can see this one is carbon, and that is due to the graphene oxide and MWCNT, and this is the EDX of the optical fiber coated MWCNT coated optical fiber. So that's why the SiO2 is also came in this EDX analysis. Okay, so in this way we can do the verification of the coating materials. Okay, so we did the several tests like stability results. We found this is the quite challenging in the many biosensing work, but stability of our sensor is quite good, and we also test the pH test and in the presence of the some acidic and basic solutions, and we found that our sensor is quite better at around 7.4 pH. So this pH is mainly for the also serum, matching with the serum, so we can show that this kind of the sensor can work for the clinical applications or the human fluids. Okay. So we have also done the reusability test. We detected the one concentration, and after several days we tested the same concentration and we found the similar response. So we did this reusability test for the two different concentrations, and it is quite effective and quite good. So similarly, we have developed the several different kind of the sensor structure and detected the same concentration, and we found that our sensor is reproducible. And we have also done the selectivity test in the presence of the other biomolecules or interference, and we found that this selectivity is quite good for this kind of the work. Okay, so in this way, we have developed the. I will quickly discuss one more work, and then I will finish before time. So that the other work is based on the humanoid shaped tapered structure. So in this case, we have detected the histamine. So histamine is a biogenic amine that can accumulate in food during the storage and spoilage, especially in fish and fish products. Okay, so accurate detection of histamine level in food is important to ensure food safety and prevent histamine poisoning. Okay, so for this purpose, we try to develop uh, uh, a novel fiber structure, that is the uh, humanoid shaped fiber structure. Here we can see this one, it look like a human head, and this is look like the shoulder, and this is look like a hand. So it is we named it as the humanoid tapered structure. So till now this kind of the sensor structure is not developed, and this is the quite unique structure, and developed by our team. And we have used the some new kind of the nanomaterials, and the results are quite interested. You can see with the help of the different concentration, we can clearly see the different peak, and the linearity range of the sensor is quite good, that is 0 to 1000 uh, micromolar, and its stability is quite good, and the pH it mainly work for the pH 7.4, that is the very effective work. And we have tested the reproducibility and reusability, that is quite good for quite good. And we have uh, also tested the selectivity in the presence of other of the biomolecules, and we found that this sensor is quite effective for the histamine, not for the other purpose, because we use the diamine oxidase enzyme that only react with the histamine and produces the changes, and not reacts with the other biomolecules. Okay, so in this way, we have developed the several kind of the sensor for the detection of the several biomolecules, and we have also developed for the creatinine, and that is very important for the chronic kidney disease, and using the multi-core fiber. And we have also used the some other kind of sensor. In this one we have also used the maxine, that is the maxine is a very important material for the biosensing purpose. And we have our team has also developed a sensor for the cardiac troponin 1 detection. I am not going to discuss these things in the detail due to the time, but if someone is interested, they can read our papers based on these kind of the biomolecules. And then we have also developed a sensor that is the MZI based sensor for the cholesterol detection in human body. And so this is the glucose sensor based on the typical single mode fiber. And here this is very important to notice that unclad fiber and single mode fiber, when we do the tapering of the single mode fiber, then its cladding diameter reduced, but at the same time the core diameter also reduced. So here we can see the core diameter, originally it was 8.2 micrometer, but when we tapered the external diameter from 125 to 40 micrometer, then its core diameter also reduced in the proportion that became 2.624 micrometer. Okay, so this is very interesting phenomena, and we have then we have used the graphene oxide. Here we have shown how the guided field ruptured on the transition region, and more evanescent field can go outside for the sensing purpose using the Assoc simulation. So we have also developed a sensor for the dopamine, and that is very important for the biological purpose, and we have also developed a sensor for the uric acid detections. So I'm going to escape these things, and yeah. So this work is very important because in this we developed the fiber ball structure, and why this is important, because in this work we have also tested the serum. We have collected the different human serum from the hospital, and we have tested using our developed sensor, as well as we have also tested with the instrument available in the clinic, and we found that our sensing performance is quite comparable with the instrument available in the clinic. So we can say that our sensor can be also used for the clinical purpose, and this is the multi-tapered structure. So we have developed the 4-tapered, 5-tapered, and 8-tapered structure. We compared, and this is the original CM figure of the different tapered structure, and we compared, and we found that the 5-tapered structure is more effective for the sensing purpose. So we have also developed a sensor for the L-cysteine. L-cysteine is also called as urinary protein, and during the kidney disease, it is mainly present, and the collagen that is also present in the skin disease or something. So we have developed a sensor for the collagen purpose. So this way, this work is the water pollutant, that is the peak aerosol, and we have developed a sensor. This is the sensing structure that is very important, sensing structure. Okay, so our team has developed a lot of the sensor. This is the most important work, but due to time I will not discuss here. That is the multi-core fiber-based cancer cell detections. So we have developed a multi-code based sensor, and we use the several copper oxide nanoflower and graphene oxide for the improvement of the sensing performance. We have compared with the different kind of the cancerous cell lines and normal cell lines, and we found that our sensor is easily able to differentiate the different kind of the cancerous cell lines, and its limit of detection is quite good. The other work is based on the bacteria detections, so that is quite effective, and that detected the Shigella bacteria we have cultured in our lab. This is very important culture process. If anyone want to do the work on the bacteria, they can refer this work and can grow the bacteria and do the any kind of the bacterial work. So with the help of this work, and this work is very effective, and its detection time is only 5 minutes, and limit of detection is 2 colony formic unit per ml bacteria. So there are several optical fiber sensor book. Like last year we have a book on 2D material based SPR sensor, and the plasmonic optical fiber based plasmonic biosensors. So if someone is interested to optical fiber sensing work, they can refer these books. So these are the few papers, highly cited papers in our biosensing work. So once again, thank you so much for your patience, as well as give the opportunity to present my work. So if anyone have a questions, you can ask, or you can, if anyone would like to do the collaboration, they can send us the email. We are really happy to discuss the work. Thank you once again to organizing committee members.
Thank you, dear Dr. Kumar, for your nice presentation. So, dear participants, do you have any questions?
How these sensors commercialized?
This is very good question. So till now we have developed the prototype, and we are working on the packaging. So as I discussed, the diameter is around 40 micrometer and less. So there is some challenges in the packaging purpose. So we are looking for the some industrial persons who are the good in the packaging. And so after that, if we have a plan to commercialize this kind of the sensor. This is a very nice question. Thank you.
Thank you, dear Dr. Kumar, again.
Thank you so much to audience and the organizing committee to invite me, and best wishes for the conference. Thanks again.
Have a nice day.
Thank you.
Elamassie, Assistant Professor at Özyeğin University, Istanbul, and Executive Co-Director of the Center of Excellence in Optical Wireless Communication Technologies. With a PhD in Electrical and Electronics Engineering, he is a leading expert in optical wireless communications, boasting over 50 publications and notable awards.
In his talk, Skies of the Future, Dr. Elamassie explores the design of a multi-layer airborne optical wireless backhaul network, integrating high-altitude platform stations and UAVs. Discover the future of connectivity and the seamless integration of non-terrestrial networks with the terrestrial ones. Join us in welcoming Dr. Mohammed Elamassie to discuss advancing wireless technologies and bridging the digital divide. Welcome, Dr. Mohammed Elamassie.
Hello all, good afternoon. Okay. My name again is Mohammed Elamassie. I'm an assistant professor at Zain University in Istanbul. I'm also a co-director for the Center of Excellence in Optical Wireless Communication. This Center of Excellence is used for experimental works. In that experimental works that span underwater visible light communication. For this purposes, we have a very large aquarium that's equipped enough to make underwater visible light communication. Additionally, we have free space optical communication. That free space optical communication for indoor environment, we have atmospheric chamber. That atmospheric chamber, inside it, we can generate rain, we can generate fog in order to test the effect of different weather conditions and optical beam propagation. Additionally, we do some vehicular visible light communication. For this purposes, we have headlamps of the car, vehicular headlamps and vehicular tail lights that we are using inside the lab for making some tests. And also we have two dedicated cars, two dedicated vehicles that we can use for visible light communication outdoor and also in a mobility conditions when vehicles are following each other. This is an introduction for an OCATIM lab. Additionally, also we have a communication theory and technology research group. That's for theoretical work. So we have one lab for experimental and one lab for theoretical. These are cooperating with each other in case someone is working experimentally and he needs some validation by theoretical works, and someone is doing theoretical works and he needs to validate his work experimentally. So we have cooperation between these two labs. So let's talk about the topic of the future, multi-layer airborne optical wireless backhaul networks. Here we are going to talk about backhaul networks. We will define what's backhaul. We will not talk about access links. So we are not talking about when the user is going to access the network. We are talking about backhaul network and why optical will be used for backhauling and why we are going to use the sky, why we are going to use airborne nodes that are in the sky for backhaul links. So in order to answer this question, we will start by defining the non-terrestrial networks, because we are not going to use the terrestrial network, we are going to work in the sky. So first, to understand what's non-terrestrial network, we need the definition of that one. What are the purposes of non-terrestrial network, and what are the possible components of non-terrestrial networks, because we are going to select some of these components. So the definition simply, we are talking about non-terrestrial, so we are talking about the object that's not on the ground, that's above the ground. So the purpose, sometimes we need to cover, for example, a rural area that's away from the network that's here, but we need to connect that area to the central network. Or for example, a moving platform, such as a high-speed train that we need to make a connection to the internet with that high-speed train, so we cannot connect it by cables. So the components, let's look at the components of airborne nodes that can be used for non-terrestrial networks. It can be satellite. It can be stratospheric nodes such as aerostatic hubs and aerodynamic hubs. It can be unmanned aerial vehicles such as fixed-wing UAV and rotary wing UAV. But which part of these can be used for the future networks and why? So we need to do some classification. So let's start with satellites. When we classify satellites, satellites are classified into geostationary axis and medium Earth orbit, in addition to LEO, which is low Earth orbit. Geostationary satellite, from its name, it's stationary, but it's at an altitude of around 36,000 kilometers above the equator. That's a very long distance. It can cover a very large area on the ground because of that long distance, but at the same time, we have to take into account that long distance means a long delay. That delay, we don't need it. So in addition to that, there's a low Earth orbit, which is the closest satellite to the ground. That's from 160 kilometers to 2,000 kilometers. And between them, there's a medium Earth orbit satellite. But what's the problem with these two types of satellites? Once we are going closer to the ground, this means that the satellite will not stay at semi-fixed position or fixed position with respect to its point on the ground, which means that in order to make a link, we need to make something else, such as the tracking, such as positioning. So once we are coming closer and closer to the ground, yes, the delay will be decreased, but additionally, that satellite will circulate the ground faster and faster, which makes some challenging regarding directing the communication link from ground to that satellite. So can we make a closer link to the satellite, a closer airborne, and also semi-fixed position? Now we came to hubs. If we look at the Earth, the atmosphere, the first layer closer to the ground is called the troposphere. The next layer is the stratosphere. The stratosphere layer, there are some airborne nodes that are recently manufactured, such as aerostatic hubs, balloons and airships, and aerodynamic hubs. These can fly from altitude from 17 to 22 kilometers. And at that altitude, the wind speed is very slow, so that we can use balloons and they can stay at semi-fixed position, so we can do communication with that one. Additionally, aerodynamic hubs can rotate in the sky in a circular track with a small radius, so that we can keep communicating with that one. Additionally, all of us know drones such as rotary wing UAVs that fly close to the ground, which means that we can control their position. They can hover at semi-fixed position. So these nodes can be used for communication without having a problem in terms of tracking and positioning. So do we really need non-terrestrial network? So let's look now at why non-terrestrial networks. The first point is that if we look at the ground, we can see that 40% of population around the world are unconnected to the internet or underconnected, which means that still some people, we need to serve them. We need to serve some areas that's still unserved. So how we can reach to that area? Can we reach it by terrestrial? Can we go to the remote area that's, for example, away from the center city by hundreds of kilometers by terrestrial network? Can we make a trenching and connecting cables underground? Okay, so this is one example. But let's look at another example. We are inside a city that's equipped by internet. All people can use that internet with a good speed without any problem. Next few years, the requirement for internet will increase. This means that the backhaul links will not be enough. Does this mean that we need to make a new trenching underground? We need to change the number of base stations, and we need to make trenching in all roads to make a new network? Okay, so these are two examples that we can use in the future, the non-terrestrial network, to support the speed of data rate that's needed. So this non-terrestrial network at the end can be used for a network, whether access links or backhaul links or backbone links. In order to make sure about that one, we need to look at some of the deployment examples. We can see that there are so many examples. For example, this Gogel Loon, which is a balloon that can fly at stratospheric altitude between 17 and 22 kilometers, and it's a project by Gogel. There's another project such as this drone by Nokia. And also here in Turkey, there's a Turk cell, a drone cell, which is also can be used for an access link. In addition to that, mega satellite, which is a huge number of satellites at LEO altitude that can be used for communication purposes. So there are so many deployment examples that can make us sure about using non-terrestrial networks for future communication. Okay, so now we need non-terrestrial network, but which one to use? Shall we use a drone? Shall we use rotary wing UAV? Shall we use high altitude platform station? And what? Now, when we look at HAPS fly at altitude, as we said, at stratospheric altitude. What does that mean? That means it's above the maximum altitude of the cloud. This means that it can harvest solar energy without any problem. So it can power itself without the requirement of coming back to the ground for recharging. Okay, so what's the advantage? This is the advantage if we compare it with rotary wing, for example, UAV. Rotary wing UAV is closer to the ground. So if there is any cloud, this means that it cannot recharge itself. It cannot use the sun energy. But if we compare it with the satellite, it's much closer to the ground than satellite, which means that a less delay. So high altitude platform stations can be used for these purposes. So some advantages of the new HAPS or the HAPS technology. We said that the wind speed at that altitude is very low. So whether we can use balloons and airships at semi-fixed positions, and we can use the HAPS with the fixed wings also by controlling its speed without any problem because the effective wind is almost negligible. Additionally, these HAPS that fly at high altitude with the recent technology, it's with a very light weight. This means that easily, without consuming that much energy, we can have a very large wings, and those large wings can be equipped with the solar cells to harvest energy as much as possible, and that harvest energy can be used for communication purposes. And there are so many applications for that. But let's look at the following example. This example, as you can see, this is a high altitude platform station that's designed by Airbus. It's known as the Virte. For one of the experiments, which is the last one, this one flies at that altitude and do communication purposes for 64 days without the requirement of recharging. Okay, now we said that, okay, so we are going to use high altitude platform stations that fly from 17 to 22 kilometers. And we know that it can support a communication for a long time without the requirement of recharging. But we need to answer the question, what's backhauling? Why we are going to use these for backhauling, and why optical link would be used. So first, what's backhauling? Maybe some of the attendees here, it's the first time to hear the word backhauling. Now, if you know, if you use your mobile, you need to access the link. So there is a base station, there is an access link for all users to that base station. But from base station to the core network, we need to carry the data of all users. So there is a link that's known as a backhaul link. So to connect a remote area, the data of all users to the core network, this is known as a backhaul link. So backhaul link carry data not just for one user, it will carry data for a huge number of users. This means that we need a very high speed link. So some people may say that, okay, you can use a fiber. Fiber can be used for very high speed. That's correct, but we cannot use fiber everywhere. We cannot use fiber to connect with a remote area. We cannot use fiber to connect with a moving platform. Okay, so as two common examples, a remote area. Look at this area, it's far away. Shall we use trenching and connect, for example, hundreds of kilometers to reach to that area? We don't need. So we can use a flying platform to cover that area. Additionally, let's look at this example. Here, it's not a large area. It's not a remote area, whatever. It's a sudden, huge data needed because there is a huge number of people that come to a specific area for just a short period of time. So we will not make a huge network that's forever there to serve this huge number of people which are going to use that network just for a short period of time. This means that we can use instantaneous network to serve this huge need of data rate. As some other examples for using drones post-disaster, we all remember the earthquake in last February. So if there is any disaster anywhere, it means that the terrestrial network will be distracted. So can we use non-terrestrial network to have a network instantaneously or within a short time to serve that area, and that can help people for rescue operations? So for example, like a cross in the ocean, we can do a backhaul link for that cross. As you can see also in the other figure, which is a concert, a huge gather of people in that area. So we can make a backhaul link for the people in that area. Okay, so now we reach to the point that we are going to use high altitude platform stations, and we can use rotary wing UAVs, and we know what's backhaul link. But the question now is about optical wireless links. So let's look at optical wireless links. First, optics simply at the transmitter side, we are going to use either light emitting diodes or laser diodes for communication. At the receiver side, we are going to use a photodetector. Simply, laser converts electrical current into optical power. At receiver side, optical power will be converted into photo current by using a photodetectors. So that's simply. What's a free space optical communication? Free space optical communication is a communication by using optical band of the spectrum that's in the infrared band. So if not in the infrared band, such as in the visible band, it's known as visible light communication. So once we hear the term free space optical communication, this is typically for infrared band of the spectrum. Okay, so the question, for example, why not using RF? RF is typically used. So we need to compare between RF and optical. If we compare between them, we can see that the bandwidth of RF is in terms of megahertz, up to several gigahertz. However, if we look at the bandwidth of optical, it's in terms of tens of gigahertz per wavelength. So it's much higher bandwidth. So this is an advantage of optical. If we look at interference, RF is prone to interference from electromagnetic waves, but optical is immune to RF interference. Again, optical is better in this sense. If we are talking about license, RF requires license, but optical is a license-free. So this is also an advantage for optics. If we are talking about multipath interference, RF is subject to multipath interference due to the reflections, diffractions, and scattering. However, when we are going to use a backhaul link, it's a link that has a good directivity. So there is no interference and there is no multipath interference because there is no reflection, or the reflection is something that's negligible. Now, let's look at the movement-induced fading. Okay, in this one, when RF link is moving, because it can cover a very wide area or semi or omnidirectional coverage, then RF in this point is better than optical. Okay, but optical with a new technology of tracking and positioning, this problem can be solved. If you look at security, okay, again, optical is better than RF. If we look at latency, RF and optical signal, both of them approximately have the same speed in atmosphere. In different environments, they have different speeds, such as underwater. There are so many advantages of optical. Now, some other advantages that are for RF, not for optical. When we look at installation complexity, RF is relatively simpler. Why? Because for optical, we need some additional components for tracking and positioning, especially when we are talking about long distance or a moving platform. So for cost, once we need more components for optical, then it requires more cost. For data rate, since optical has a larger bandwidth, then optical is better in terms of data rate. And if we talk about reliability, we may say that, okay, RF is better because optical, especially infrared, it will be affected by weather conditions such as a cloud or fog. So, but in most of these advantages and disadvantages, we can see that optical link is the optimal solution to be used for high-speed communication. Optical communication, there are two main types of optical communication. One of them is known as a coherent communication. Coherent detection. However, the most common one is based on IMDD, which is known as intensity modulation direct detection, which is just we send information by changing the intensity of the light, and we receive the information by direct detection by detecting that change in the intensity of the light. So for this purpose, we use simple modulation techniques such as on-off keying, unipolar pulse amplitude modulation, and pulse position modulation. Laser sources can be used, and light emitting diodes can be used. Also, different types of detectors can be used for communication, such as positive intrinsic negative detector, and also avalanche photodiode. Amplifiers can be used. Now, we reach to the point, after understanding what's backhauling and why optical is needed and why high altitude platform stations can be used, let's come now to talk about the structure of that backhaul link for different areas. Now, shall we use a multi-layer to make backhauling for an area, or can we use a single layer? Is it different if we are talking about rural areas or remote area or not? And can we answer several questions? Do we need high altitude platform station 1 track, 2 tracks, 3 circular tracks, and how many? In each track, how many high altitude platform stations shall be used? At medium layer, how many rotary wing UAVs shall be used there? What's the altitude of that one? Number of laser sources that will be equipped with the high altitude platform stations. How many? How many number of laser sources will be equipped by medium layer rotary wing UAV? And also, if you look here, we add another rotary wing UAV. Why this one is added here? If we are talking about inside the city and there is a building and there is a rotary wing UAV that needs to communicate with base station, if we have a large building, this means that some of the links may be blocked. This means that we may need a support of some low altitude rotary wing UAVs. So we need to answer all of these fundamental questions. Now, let's start with a single layer design. Single layer design, if we look at rural area, base stations are typically large. Few number of base stations. There are no large buildings to block the line of sight link. So it's expected that single layer is enough. But how many layers we need? How many hubs at that layer we need? We need to answer this question. In order to start by this one, we try to look at geometry of the problem. We try to arrange the cellular cells which are hexagonal in shape. And we can see if we have 3 numbers or 6 numbers or 9 numbers of hapses in that track, as you can see at any point, the distances, the arc length between them is the same. All of them will see the same distribution of base stations. This means that at any time, the handover, because these are continuously rotating, which means that the link will be handed over from one hubs to the following hubs. So by using 3 and multiple number of 3s, that would be good to have a handover or a seamless handover. As you can see, when hubs is flying, it communicates with some base stations on the right-hand side and some base station on the left-hand side. This means that the track, which is a dashed line, can cover an area which is larger than the dashed line that's by solid line, as you can see here. So by looking at the cell radius, we can understand what's the radius of that track, and we make a function for the first track, second track, and whatever the number of track. And also, by knowing the track radius, we can know the area radius, or the radius of the area that's covered by single track. Then we can know the radius of the second track and the radius of the area that's covered by 2 tracks, the radius of the third track, and the radius of the area that's covered by 3 tracks, and so on. Okay, now let's look also at this figure. As you can see, we need to serve all of the ground base stations. So at least each hubs will have now, because we have 12 base stations as an example, and we have 3 hubs, then each one can use 4 laser sources to serve all of these base stations. But is this enough? Maybe this is not enough. Let's look at the next figure. These hubs are continuously in rotation. At one point, it will leave the old base stations and let the new one to communicate with them and start communicate with the next 4 base stations. This means that at this point, the hubs should have at least, in this example, 8 number of laser sources. This means that the number of laser sources should be double of the number of base stations. So here, the number of base stations in the first track, second track, and so on for odd tracks and for even tracks, and number of laser sources, it will be 2 times number of base stations. Now, we need to cover a rural area. So we have an algorithm. In that algorithm, the input are what's the maximum allowable cell radius. What's the meaning of maximum allowable cell radius? In rural area, whatever the radius, the number of people in that area will be limited. However, the cell radius will be determined based on where the signal can reach before the signal to noise ratio drops below a specific threshold. So there will be a maximum radius. And also, what is the total area to be served to know how many base stations we need, how many cells we need. And also, what's the maximum number of laser sources perhaps? If you remember the example, we said that we have 4 laser sources or 8. Imagine that you need 8, but your hubs can carry at maximum 6 because at the end there is a maximum payload. So we need a maximum payload as an input. So if we cannot use 3 hubs with 8 laser sources, we may need to use 6 hubs with 4 laser sources per each hub. So in this algorithm, we have several outputs. That algorithm carry the radius of each cell, the area of each cell, the number of hubs that are needed, and the number of tracks that are needed. So let's go to a numerical example. In this numerical example, we consider rural area. The area is 3,000 kilometers square. Cell radius is 10 kilometers. Number of cells to be covered to cover this area by this cell radius is 12. Payload 8 laser terminals. And we also used one of information from commercial products that hubs speed is 9.5 meters per second, which is around 34.2 kilometers per hour. By using that algorithm, we can calculate number of hubs tracks are just 1 track is enough to cover that area. And in that track, we need in total 24 laser sources. So by using 3 hubs, it's enough to use that one because as you can see, the payload from this example is 8 laser sources. So 3 multiplied by 8 is 24. The other point that we need to calculate, which is the handover, because the link needs to be handed over from hubs to the following hubs. So we can check what's the arc length from the radius of that track and the speed, and we can calculate when this hub will reach to the point of the following hubs, the distance between them. And simply it can be calculated, and we can find that this distance based on that speed requires the handover to be each 73 minutes, and that's very good. So it means that if you make a call, you will not feel that call will be interrupted and handed over each second, for example. And you may feel that when you are driving inside the car and you make a call, sometimes you feel your call like a connection, like interrupted and then come back again. This is because of your movement, and your link is handed over from one base station to another one. But you don't want this one to be happening frequently. So if we consider the same example, the same area, and everything the same, but this time, maybe the power of that base station is not that high, which means that the cell radius may be smaller. So let's consider a cell radius of 5. This time, the area cannot be covered by 12 cells. Now, the area will be covered by 48 cells. If we check the 48 cells by using that algorithm and all of the constraints that we have, we found that we need now, instead of 1 track, we need 2 tracks. First track has 12 base stations. So first track, total number of laser sources that are needed to be carried out by all hubs in the track are 24. And for the second track, we need 72 laser sources. In the first track, we found that 3 hubs are enough. But in the second track, we found that to serve all of these laser sources, or to have all of these laser sources to serve the total number of needed base stations, we need 9 hubs. If you remember, in the first example, the track radius will be larger. Now the track radius will be smaller. This means that the distances between hubs is smaller. Now we can see the handover is 36 minutes, and for the second hub is 30 minutes. Okay, in this example, we talked about rural area. What about urban area? Urban area, base stations are small and much smaller than rural area, because previously the base station, the radius will be determined based on where the signal can reach before the signal to noise ratio drops below a specific value. But now it's something else. Now the base station will serve a specific area because of the density of people, because it can serve number of parallel people at the same time, simultaneous number of people. So if you have a large area, this means that you cannot serve people. People may need to make a call and then they cannot find any channel. So this means that if we use just a high altitude platform station, one of the things, we may not have the ability to reach to the base station because some links will be blocked. Additionally, we may need a huge number of tracks at high altitude. So we said that, okay, instead of that, we can use virtual in-the-sky cellular system by using rotary wing UAVs. Each one of these rotary wing UAV can serve several base stations, and they can have at the end, like in-the-sky cellular cells. Then these in-the-sky cellular cells can be considered as if it's rural area and can be covered by high-altitude platform stations. But additionally, there is another issue. As you can see, the link between rotary wing UAV and the ground-based station sometimes may be blocked because of high buildings. So we need to know what's the altitude that we have to put these points in order to have a specific probability of line of sight that we need, in order to determine how many low altitude that we need. So there are some functions in the literature, and especially this one. This one, it has several parameters, such as the ratio of built-up area to the total area, number of buildings per kilometer square, and also buildings height distribution. If you have a higher building, this means that the probability of line of sight will be decreased, which means that the probability of blocking will be increased. So let's look at these parameters by some examples. In the first example, we will consider the mean of building's height. First, we consider mean of building height 50 meters, like the average building height 50 meters. And we try to compare if we decrease it and if we increase it. So this is the mean of building height, which is 50 meters. And we can see that the rotary wing UAVs should be at altitude less than 400 meters in order to have a probability of line of sight 0.9. If we have a higher number, if we have a higher building or average building height is higher, we found that the rotary wing UAVs needs to go higher in order to have this probability of line of sight. But don't forget that rotary wing UAVs, how it flies? It flies by pushing the air down, which depends on air density, which means that it has a maximum altitude that cannot reach. This means that if we reach to that altitude and we cannot have the 90% that we need to do something else, like increasing number of rotary wing UAVs in the sky. As you can see, this one is fixed point. Now we compare with other things now. Now we are trying to look at the ratio of built up area to the total area. First, we consider it like 0.4. This means that 0.4 or 40% of the city is full of buildings, and we have other areas such as roads, streets, gardens, and whatever. So 40% of the area is full of building. Okay, and we found that, okay, we need to have a 90%, we need an altitude of less than 400 meters. However, if we increase the number of buildings for the area up to 60%, we found that the altitude of rotary wing UAVs needs to reach around 500 and close to 500 meters. And if we decrease the density or if you go to the area with less density of buildings, we found that the altitude can be less. As another parameter, which is number of buildings per square meters. So first we consider this one, which is 1,000 buildings per square kilometers, and we found that, okay, we need this altitude. However, by decreasing this one, we found the altitude that we need is less. For this purpose and for this area, which is urban area, there are so many inputs now to the algorithm, not just one input, which are maximum allowable cell radius and total area to be served, and maximum number of laser sources per HAPS, which is maximum number of laser sources for those HAPS that fly at stratospheric altitude. Additionally, maximum number of laser sources per middle altitude UAV, and maximum allowable operation altitude of rotary wing UAV, required probability of line of sight. average number of buildings per kilometer square, ratio of built-up area to the total area, mean of building's height, the height of receiving unit on the top of base station. So out of all of these parameters, we have algorithm. In that algorithm, we can calculate several parameters, such as what's the number of cells that we need in that area, what is the maximum area for the cell, what is the minimum number of cells that can be used in that area, and we can calculate also at the end number of cells or virtual cells, which is number of rotary wing UAVs at mid-altitude layers. And we can calculate also the number of ground cells, calculate the number of tracks and number of habses in the track, and we calculate all of the required parameters. Now, during calculation, we may reach to the point that the probability of line of sight that we need cannot be satisfied. So then we need to update, for example, number of rotary wing UAV to increase them in order to increase the probability of line of sight by also decreasing the altitude. So these are for backhauling for rural area and urban area and why we need a multi-layer. To this end, I will talk about the challenges, which is for future works, challenges with airborne FSO channels. Let's look at this one. As we said that at any moment, one of these hubs will communicate with the ground base station. This hub is continuously rotating. This means that after a time, another hub will communicate with this base station. There may be a link also between a core network, which is far away from this track. It's inside, for example, it's inside the city center. So it's far away if this is a rural area or if this serves a rural area. Also inside an urban area. This one can communicate with the rotary wing UAV, can communicate directly, for example, with base station. This can communicate directly with this gateway. But as we can see, it's in continuous move. So what are the problems of this one? Let's look here. At one position, this one, it will start communicate with the node. This node can be gateway, can be base station, can be rotary wing UAV. So at this point, we'll start communicate. Until reaching to this point, it will hand it over the link to the next hubs. If you look here, this is from the top view. If you look here, the track radius is in terms of kilometers. This means that the horizontal projection of that distance will be changed continuously. This means that the link distance will be changed continuously. This means that what? This means that the strength of received intensity will be changed. Okay, so this can be considered as another source of fading. So this for this link. So what about the other link? What about this link, which is a rotary wing UAV? Rotary wing UAV, this fly at troposphere, close to the ground. So it's not a fixed on a building like an FSO link between two buildings. This one is a fly in the sky. This means what? This means that it will not be fixed. It will be semi-fixed. This means that it will move horizontally in X and Y plane. And also, it will have some rotation. That rotation, it could be, for example, such as rolling, yawing, and pitching. So those 3D rotation and 2D movement, this will affect on the received link. For example, and also if you check that this movement at this altitude and this movement, the same movement at a higher altitude, the center is the same. And here is the photodetector because of movement. So the photodetector is not in the center of the received beam. But there is another movement which is related to rotation. This is also somehow more difficult because here, if there's any movement, it will result in XY movement here at the end on the spot of the received beam. But the higher the altitude, the more the shift of the beam from the center of the photodetector, because higher altitude, it will change the axis of the beam, which means that the beam itself will be away from the spot. The spot of the received beam will be away from the photodetector. So there are so many challenges that we need to address. So let me go to the conclusion. Now, the latest generation of hubs offers numerous advantages over LEO satellite, especially in terms of staying semi-stationary at semi-fixed positions such as balloon and chips, and also it can rotate in a small circular track. And in addition to that, the delay is much less than LEO. FSO stands in favorable position as a high-capacity connectivity solution for cellular backhauling in the sky. There is a trade-off between the number of hubs per orbit and number of laser sources per hub. Now, while single layer could suffice for airborne backhaul for rural area, as we can see in urban area, we may require more number of base stations, more number of layers. Airborne FSO channel presents several challenges as we observed in last two slides, and this needs still to be addressed. Here I'm talking about recent journals about these topics, which are, most of them are submitted, 3 of them are submitted and are under review, and one which is about the last challenges, which are going to be submitted soon. Thank you for your attention. And if you have any question.
Thank you very much.
Yeah.
First of all, are these multi-layer HAPS systems used nowadays?
No, still under research.
Under
Actually,
research, right?
we are just submitted one paper for this one, and we are going to submit more papers about solving the challenges of that.
Are you considering the environmental effects?
There are different things. Now, if we are talking about system layer design, such as this one, we are talking about what is the number of hubs that we need, what's the number of tracks that we need. First, we will not, this is the typical number before considering any weather conditions. Now, if we need to consider now weather conditions, we may say that, okay, instead, okay, if we need, for example, number of rotary wing UAVs is 20. Okay, what about weather conditions? If the link is blocked, we may need to support that one by additional another rotary wing UAVs to make a change of the direction of the link, or we may need to support that, for example, by the new technology, such as reconfigurable intelligence services to change the direction of the link for weather conditions. But this is a system level design. This is for typical conditions without the other effects.
Are there the human health for this system?
At the end, this is not an active link, so it's not for a human. This is a direct link. That's, for example, from base station to the gateway. So it's not a link that's for a human. So it's not for access link.
So you are not increasing the base stations. Right?
No. And I'm not dealing with the link between a human and base station. This is between base station and core network.
Okay. Thank you.
Any other questions, please? Okay, thank you.
Thank you very much for your inspiring presentation, dear Dr. Mohammed Elamassie. So our next presentation will be at 5 p.m. so we can have a short break again. See you at 5 p.m.
To introduce you, Professor Martin Virte, distinguished member of the Brussels Photonics Group at Vrije Universiteit Brussels, Belgium, with a PhD earned with the highest honors in 2014 and a 3-year postdoctoral fellowship. He became a research professor at VUB. Today, Professor Virte will share his insights in the talk titled Integrated Multi-Wavelength Lasers, Design, Control, and Applications. Please join me in welcoming Professor Martin Virte to share his profound insights.
Thank you very much for the kind introduction. I hope you can all hear me well. Yeah, if nothing is reacting, I guess that's the case. So as introduced, I will give try to give a reasonably long presentation, so not trying not to exceed the time allowed. Will do my best for that. And mostly about some research work we have been doing with my team, mostly with thanks to the European Research Council funding, so on the project Color Up. So I would like also to thank, the organizer for inviting me. I'm very honored to speak here today. I would like also to thank my team for their work and for making work quite enjoyable, I have to say. So before diving into the research per se, I would just like to highlight very quickly my team, so the Brussels Photonics. So it's not what I'm saying that there is different distinctions. So some people call it the team, and then we have smaller groups, or we call it the group, and we have smaller teams. So that's depending on the people. So when we are speaking about the Brussels Photonics team, it's the bigger entity. So it's our department at the VUB, and we have more than 50 researchers. And so if you, that's one picture of our campus, so Photonics campus, and you might think that, well, it's very green for Brussels, even though Brussels is supposed to be a capital city, simply because it's not really in Brussels. So it's we are a bit 20 kilometers away from Brussels. So that's why we are enjoying such a green scenery. And what we have here, why we have this special, this special building is mostly to host our pilot lines for manufacturing. So I'm not directly involved into this, but if you have any question, I would be happy to forward them to any of my colleagues. What is also quite important is that we recently secured funding to get another building that will be twice this wall side, that will be next to it, so we can't see it in the picture, where we will move all the other remaining labs. So it's we are enjoying, are quite fortunate at this level to enjoy really a lot of space, even though we are in the heart of Europe. Just a quick highlight, mostly because that might interest, I guess, some of you, mostly on the application and the fabrication side. So we are fully capable of manufacturing any kind of freeform optics, in both in polymer and now in glass. So we got recently all the equipment necessary to work with glass. So for example, with the glass press molding. So we can really control the full chain to produce any kind of micro or freeform optics as necessary. But this will not be the topic of my talk, because what I'm doing mostly, I'm working in semiconductor lasers. So though my colleagues are doing an amazing work doing with this freeform optics and optical design, I'm not directly involved there. So, but I think it's always important to highlight the features of the group. So if I jump back to the technical aspects, so it starts with I would say, very basic aspect. We've all learned, and we keep learning, because that's still true, that a laser is normally a single wavelength light source. That's why we are actually using them. So we don't want other light sources, other wavelength appearing. But under certain conditions, so some people call it typically multimode lasers, we can have, of course, multimode lines of laser line that are occurring in the single device. So what we are trying to do here is to go a bit beyond just this problem of having a multimode laser, which is often qualified as just, okay, we have a bad laser, but it's kind of works, so it's sufficiently single mode for us. So what we are trying to do, we are actually trying to really control this multi-wavelength aspect and try to see, okay, can we harness it instead of just as everyone else, complaining that this exists and how to kill and maintain only a single wavelength. Could we exploit this multi-wavelength aspect and take advantage of it? So that's really the main aspect we are looking for, and try to turn, let's say, this beautiful picture, not from us, unfortunately, but I would have loved to have this. So just to highlight that we really would like to go from just a single wavelength laser to have an independent and controllable multi-wavelength laser. So when I'm working, since I'm working mostly on photonic integrated chips, and so with colleagues doing a lot of integrated optics, a question that often comes to mind, and okay, why not simply combining these different lasers? So then, in a sense, here we have a simple incarnation of a multi-wavelength laser. So what is, however, missing here is that, of course, we have two lasers side by side, and if they are on the same chip, well, basically, we have a multi-wavelength laser. The problem is that we have no coupling between these two wavelengths. And as we will see, the coupling is what makes all the advantages of these devices, because if you want to exploit them, so for instance, if you just want to create a bit node between these two lasers, if you use this kind of setup with just two different lasers, you're just adding the noise of the two. If you use a multi-wavelength laser where you have two wavelengths generated from the same cavity, you will actually have a coupling between the two noises, noise streams, and you will have a much better noise properties when you're looking at this the bit node that is created. So even in the case where you just want to use two wavelength or three wavelength output without much tricks done to the laser, it is advantageous to work with a multi-wavelength laser. So the first step, that is, of course, and that's where we started. It was, I would say, already, if I'm trying to think about it, already 6-7 years ago. Simple question. We also said, okay, how to get multi-wavelength emission? At this time, we're working with quantum dot lasers, and so you might be aware that quantum dot lasers, some of them can emit at 2 wavelength. And we were thinking of, okay, how could we test and to push a bit this idea using, for example, photonic chips. So I'm going to very quickly review one of the main challenges here on simply how to get multi-wavelength emission using a generic platform. So that is literally something that we could all virtually use. So I summarize it mostly as, okay, 2 main options to get multi-wavelength emission. And I think you will quickly agree with me that it's quite logical. So on one side, the option is to have intracavity wavelength selective elements. So that could be DBR, that could be if you have something in free space, that could be any optics that is selecting like grating, for example, traditional grating. So that's definitely possible. So all these optics that are filtering, could work here. In this case, what is readily available on most platforms that we have for photonic integration are DBRs. So that's why I'm showing them, but it's not really limited to that. So of course, if you have these 2 DBRs, and you could easily imagine that you add more, like 3, 4, 5, 10 DBRs. I cannot guarantee the performances though, but in effect, your cavity would be selective in terms of frequency, and you could achieve frequency, multi-wavelength emission eventually. Another option that is somehow connected to that is using quantum dot as gain medium. I mention it here, though there is no real wavelength selective element, but I worked a bit on there, so that's why I'm mentioning it. But mostly the gain is restricted to much narrower states. So I'm not going to go too much into the detail. I'm not that competent about quantum dots as a gain medium. But in essence, you would, instead of having a broad SOA gain that you try to filter and to lock into smaller windows, you would only have gain in these smaller windows. So somehow it works as if you had a wavelength selective element. So that's one of the options that we have. So the other option is to use, for instance, external forcing. So in this case, what is shown here is, I would say, arguably a bit more complicated, but not that much. You can use a broadband laser. So in this case, it's just a ring laser. It could be also that has been demonstrated by the same group with a normal Fabry-Perot laser. So you already have a laser that is already broadband. So you have a broadband emission. And what you create, you have some filtered feedback that is represented here. So here you have array waveguide gratings, which are basically gratings in an integrated photonic integrated circuits. So they are splitting the output in 4 different channels, and each channel is equipped of an SOA gate, so literally just an amplifier. And this amplifier is going to select which mode receives feedback. So with this, you can trigger 4 different wavelengths quite easily. And it's quite effective. So, but there are a couple of difficulties, as you will see here. Mostly that, of course, the design is a bit more complex, also because these elements, so the arbitrary waveguide gratings, are more difficult to combine and to design. Also because they take way more space. One also a big difference, but I'm coming to that in the next slide. So one of the big difference is also in terms of robustness. So if you compare these 2 options, so the intracavity filter on one side and the external forcing on the other side, The external forcing has the advantage that it's extremely flexible, since you can control, if we quickly go back, I mean, if you can control each gate separately, it's very easy to select which one is going to be amplified, and you can directly imagine which is working quite nicely to have multiple emission by just finely tuning each of these gates. So this works very well. The downside is that the current at each gate needs to be very precisely set. So meaning that if you have any external perturbation that is adding to that, then you risk having a complete switch, I mean, or to lose completely your stable output that you were selecting. On the other side, these options, so the intra-cavity filter, you don't have that problem at all, but in the reverse situation, you have absolutely, I mean, almost no control. So as you see, I mean, when you have such a simple device, of course, you can try to inject some current into the DBRs that is going to make them shift a bit, but it's not really efficient way of controlling them. Same thing for a quantum dot laser. So in the end, the only thing that remains is changing the current, for example, for the gain medium. But if you're changing the current, you're changing everything at once. So you're changing how much carrier you have in the population. You're shifting the gain, and so it's a relatively bad way to control the laser. So initially we faced this, this trade-off because we thought, like, okay, we want to have multi-wavelength laser. What makes sense and which one could really be exploited? It happened that in our work, I mean, so we went with the option one, mostly because one of our initial idea was to develop a method to control multi-wavelength lasers. So I will come to that in an instant. But of course, in this context, if we have something that is less controllable, okay, that kind of makes sense to go with the most robust option and hoping that we would control them afterwards. This was still a gamble, and retrospectively, I think we should have gone a bit with some of these a little bit as well to make it to be on the safe side. But okay, well, we were a bit lucky, and it finally worked without too many difficulties. So to control these multi-wavelength lasers, we went with a relatively, just a first example of this multi-wavelength laser that we got. As I mentioned to the young lady and the rehearsal, I mean, I'm not completely at 100% today. I'm feeling slightly unwell. No worries, I can still present, but I might be a bit sluggish. So my apologies if I jump a bit weirdly from one slide to the next. So that's an example of the dual wavelength that we implemented in the end. So as it's a summary of the previous slide in the end. So where we have the advantage that we have, of course, this design is simple enough that it's reproducible, so it can be easily picked up by other groups. I mean, so if you're interested, let me know. We have also a relatively flexible wavelength setting, because just with the 2 dBrs, we are still constrained at some step of the design, but we could place them 20 nanometers apart, 5 nanometers apart, so there is no major constraint here. And but I say also small tuning range for the dBrs. This is a bit at the limits of in the end, because we see that it's also decreasing the reflectivity quite a lot. So as soon as we're trying to tune them, the reflectivity drops also, which decreases the performance of the laser. So perhaps not ideal. And then I would say one of the major drawback is that we can only control on this particular platform, which is great, but we can only control the dBr length. So we cannot really control the index contrast or the coupling, which is okay, good, but you have to be a bit careful at this design stage. If we go now a bit in the difficulties really for the design, you will see that dBrs are actually our main issue. And it's why I mentioned just before that, well, yeah, we are a bit constrained into what we want to achieve. So if we just take the gain medium, so that's the gain curve, and we just close the cavity, so we end up with something that you probably all know very well. So we end up with this comb of longitudinal modes. So we have just a different longitudinal mode that are allowed in the laser. And what we are going to do with the dBr, we are trying to just select one in particular, and we hope that we will achieve lasing. Of course, in practice, there is a trade-off. we need to make sure that we encompass maybe a few modes a few longitudinal modes to make sure that there is only one that is fitting, and so on. But okay, it works quite nicely in practice. With the second DBR, of course, we want to do the same thing, but you can directly see here that the dashed line is actually the SOA gain. I mean, the gain of our gain medium, and at one current, and the black line is at another current. So you then directly see that depending on where you are, if you're with the black curve, so at a certain current level and higher current level, then everything is nicely balanced. But if you are at a lower level, then probably you will have some imbalance. And in the end, what we see without any control is that we end up with a laser that is often experiencing switching. So we have an unstable behavior. So we end up with dual wavelength emission, but it's not really stable enough to be exploited. I mean, and as you see, so there is clearly a mode competition going on until we only get this blue mode, and that's it. So that's a bit a constraint. So the thing is that with this platform, we're also quickly reaching the limit of the DBRs, mostly because this separation in characterizes the bit node that we want to achieve. So if you want to work with dual wavelength lasers, you might consider that, oh, well, I need one wavelength and the second wavelength at a random position. So let's say 1550, and then the other one being rather independent, 5070. But as soon as you put it in the context of, let's say, terahertz or millimeter wave or communication, then the bit node becomes very important. You want to be able to set it at a precise separation. So we are typically working in this context, so we want to work with this bit node typically between 50 and 50 gigahertz and 1 terahertz. So we also need to work with a channel separation, which is basically the smallest separation that we are working with right now that is realistic, or for application is from 2 to 10 gigahertz. So we end up with more realistic, say, something like this. So which is, as you see, instead of selecting one longitudinal mode, we are now selecting way more. And finally, the cherry on top is that the DBRs actually have a fixed bandwidth of about 100 gigahertz. So in practice, we get something like that. So if we want to design something that can really be used for application, well, we will need to push it a bit further to avoid falling into this kind of constraint. So in short, so DBRs are convenient. So we can make it work. So we can achieve dual wavelength emission. But the flexibility is a bit limited. I hope that it is for now that our partner at the foundry are going to be able to improve the work, their platform, and that it's only going to be temporary. But okay, I'm not in control of that. Typically, long cavities are required to achieve narrow mode separation. So if you want to be able to have like different modes, different channels, so to work with this laser, for example, for communication purposes, you will need very long cavities, which comes also at a price. So typically, you will have higher losses. The footprint is going to be significantly bigger. You might need also more amplifiers to make it work. So which is also going to decrease the power efficiency and so on. And finally, the external control is clearly required. Without it, it's not going to work at all. Simply it might be robust, but it's not going to be controllable enough to be realistic. So that's where our first step, was to make these lasers, and our second step was to try to control them. So that's actually where I think we started our contribution, really. For the design, it was not something cutting edge. It was trying just to bring things together. I think it's important to mention because, I think that's any person who started their own lab. They know how it works, and that you start with a few years of struggling, just putting everything into place. So not necessarily groundbreaking work, but it's a time that is really important to spend trying to build things. And so we spent it trying to build these dual wavelength lasers, and then we tried to control them. Well, I'm saying that makes it really sound like, oh well, we had this multi-wavelength lasers delivered, and then we worked in the lab to control them. I mean, it's a bit of a stretch, because actually the solution that we came up with is integrated as well. So since we cannot change, I mean, once the chip is done, it's done. We cannot modify it at all. So we actually needed to also include that at the design stage. So lucky for us, I mean, we didn't have to make too many runs, because one run takes about a year. So, but I mean, it worked quite quickly, even though the first one was a big fail, I have to say. But the second one worked quite nicely. So what we designed, what we tried to do for to control these lasers is just to have a small external cavity. So I mean, this idea, if you have just you add a third cavity, or say, I mean, in this case, that would be you consider that you have two distinct cavities here, and you add a third one as a tunable cavity. That has been demonstrated multiple times in free space or in other type of the devices or settings, but mostly as a way to switch very efficiently from one wavelength to the other, or even to have a tunable laser. So even, I mean, a continuously tunable laser. So in our case, one is very important, that we only used a very weak feedback. So I don't think it's mentioned in this slide, but here we only have an 85-15 splitter. So this reflector, this broadband reflector, is only about 40%. So same thing here. I mean, it's might be from 50 to 70%. So in total, we are only sending back not even a few percent of light to the laser cavity, and we are still controlling it with another amplifier that most of the time is used to actually, I mean, suppress even more the feedback. So we are working with a very weak optical feedback, and so not to control at all, like to get full switching, though it works, but mostly the idea was to say, can we stabilize the laser? And so what we observed, it works very nicely, a bit too much to our liking, to be honest. I will come to that in an instant. But we were able to have, just with this weak optical feedback, to have drastic switchings between the two modes. So as I said, well, our point was not necessarily to control just which wavelength is emitted. We wanted also to balance it. So that was a bit working a bit too much for our plans. But we still observed that in some cases, or by decreasing the feedback strength, we could adjust. So for example, around here, we could adjust the voltage control to kind of select the two modes at the same time and have a good balance process. So overall, it worked a bit better than expected, which is, well, really actually something that is bad, even though in our case it was a bit in between. And we were also very surprised that without particular attention to RF controls, that means that on chip, if you really want to do it fast, you probably have to shield a bit your different components and so on. In our case, we just use DC components, and we were still able to achieve very fast controls. So in the order of tens of nanoseconds for the switching between the two modes. And so we are quite confident that with proper optimization, we would be able to reach the sub-nanosecond, the sub-nanosecond performance. Though, to be fully honest, right now we designed a few cases, well, a few chips, and we are now waiting for manufacturing to finish. So unfortunately, for everyone working with chips, this is a bummer. I mean, we always have to wait for new chips. That's the way it is. So we have, I mean, if I come back an instant to that, so we have these two modes. We can switch nicely between them. So how does it work? I mean, that's something that I did not mention, should have maybe, that this external cavity is actually designed to select, I mean, act very roughly as a Fabry-Perot, since we have a very weak optical feedback cavity, so we don't really have resonance in there. But it still acts as a weak Fabry-Perot because we are designing it so that one mode is going to be in phase, while the other mode is in antiphase. So the other wavelength is in antiphase. So when we control the EOPM, we can effectively change which mode is resonating in the cavity, and we are forcing the switching. The question we had quickly was, okay, how many modes can we control with this technique? Because it seems great if you have one mode in phase, one mode in antiphase. If we add more, we quickly suspect that it's going to be a problem. Actually, we found a few cases where by turning a bit, by twitching a bit our devices, we could trigger additional longitudinal modes. So as you can see here, so instead of having just one nice emission at each wavelength, we had this extra red mode that was popping up. And so, sorry, with this new settings, we saw that we were able to switch actually between 3 modes. It was interesting also for us because, I mean, for us especially because the feedback cavity was not adjusted for controlling these different longitudinal modes. So as I said, we designed it so that this wavelength here and this wavelength are in antiphase in the cavity. But so, I mean, we even checking the numbers, I mean, these two are not in antiphase. And even though this was not the case, we were able to achieve a nice switching. We even found a case where 4 modes were working. But in this case, I mean, the parameter range was quite restricted. Typically, we observed this kind of beating. So when we pushed a bit the laser to be in the not in the good quality operating range, we could observe this kind of competition between, like in this case, 4 modes. Sometimes these other longitudinal modes are also appearing, and we see that, well, all modes are kind of popping up and emitting and switching with the EOPM voltage. It was, of course, a bit at the limit of what we could control, since unfortunately everything, as I said multiple times, everything is on chip, so we cannot change the feedback cavity. It's fixed, and we have a limited control over these parameters. It raised one important question in our case, is about this coupling between the different modes. So how come we end up with such a competition? What is really driving this competition? And something that has been actually studied, no, I wouldn't say a lot, but it has been already studied a little bit how this mode competition takes place in lasers. And so has been shown also, by in a past time with some other colleagues. So we show that, and I'm not co-author of this paper, but this was a more recent paper that was also very nicely showing a similar result, that this mode competition happening in a laser can trigger instabilities and even chaos. So we know that there is coupling. So there is a connection between these different modes. So the question we really ask ourselves, to which extent this coupling is actually impacting our control. Should we have a stronger coupling, a weaker coupling, and how to do that? And actually, we came looking into literature. Of course, we are all doing that, but sometimes you have to hunt for the right result. We saw that back in the 80s, there was already this condition that was highlighted. So the condition for simultaneous dual wavelength emission. And it was fairly simple that, well, the cross saturation between the 2 modes, so in effect, the coupling between the 2 modes should be actually smaller than the self saturation. If the coupling between the 2 modes is too strong, then we don't get simultaneous emission. So to get simultaneous emission, we need to have a sufficiently low coupling compared to the self saturation. At the same time, it's pretty obvious, as I just mentioned, that if we have a very low coupling, it's as if we had 2 lasers side by side, and that's not very useful for our applications, the applications we have in mind. So there will be a trade-off in there. Following this publication, there has been a few work where people estimated the minimal separation between wavelength to achieve simultaneous dual wavelength emission. And so what is quite interesting is that it was first estimated at about 0.5 terahertz, later on by 1.6 terahertz. And then people tried it. Of course, you see it much later, but people tried it and they achieved 70 gigahertz in this case, or 480 gigahertz. So significantly lower than the limits mentioned by the theory. in our case, what we observed is also we had this, it's other device. So we had, previously we had this device with a 10 nanometer separation. And so we had this different device with a third DBR. I'm not going to go too much into the detail, but the idea was to have only 1 nanometer separation between DBR1 and DBR2. And in this case, we only achieved about 120 gigahertz separation. And interestingly, it was just impossible to reach simultaneous emission. So the only thing that we could get, even with our control technique, was only complete switching. So it kind of suggests that we were mostly on this, in this, past this minimal wavelength separation. Even though that we see that 70 gigahertz has been demonstrated, we are stuck at 120. So definitely something that we need to work on to clarify this topic. To close a bit this first aspect about control of multi-wavelength laser, there's still, we show that it works, but there are still quite a few questions that we would like to answer. So it's going, it's progressing, not necessarily as fast as we want, mostly because we are waiting a lot for chips, but it's progressing. And so we start to have a bit more answers to this, I think, essential question. But as you can see, we still have a lot, and so there are also some very fundamental one. Like for instance, if there is an optimal coupling, and then comes the question how to fine-tune the coupling between different wavelengths. So I will definitely not have time to go in this direction, but that's definitely an aspect that we are quite looking into. So if I now try to bring that to the application. So, I mentioned a couple of times that, well, multi-wavelength lasers, well, they're great. We can do things. Maybe you already have in mind something that, well, we could do with multiple wavelength. So something that has been done quite directly, almost directly with multi-wavelength laser was to use them to create high-frequency bit nodes. So the advantage is that if you end up with only one device and you send it to a photomixer, you can trigger, it's relatively easy because you can trigger any kind of high frequency signal that you want. It is the case because simply to trigger a few terahertz, a frequency difference of a few terahertz for photonics it's business as usual, but for electronics it's extremely high. So if we combine the two, simply just sending these two wavelengths on a photomixer, we end up with a very high pitch, very high frequency signal, which can also have a relatively good purity compared to other competition. The main difficulty here is that, of course, the photomixer, the efficiency of the photomixers are not so great, so there are some limitation, but we have also seen there's been quite a lot of progress there. So in our idea, we wanted to go a bit further, try to see if we could have something of a bit more of a disruption in this using these multi-wavelength lasers. So we were more looking into ways where we could really harness the competition between modes and try to do, and we went into the direction of signal processing. So the idea being, or information processing, which could work as well. So the idea would then be to use these different wavelengths as different channels and try to see if we can add information in one mode and then do some, let's say, I don't think the computation would be the right term, but do some kind of computation or, let's say, processing of this input signal. What we did recently, though, is connected to optical frequency combs. And so what we were able to show is that, well, we could trigger, not broadening per se, but what we call spectral multiplication. So that's where what I'm going to present right now. So I'm going to be brief here, also because I think that's, some, or if not all of you are perfectly knowledgeable on this aspect about optical frequency comb. And but something that has been very much studied, is frequency comb, how well, it's even earned a Nobel Prize to Theodor Hensch, which is, so it's a great field, very, very active field, and a lot of things are possible. It's amazing. Right now, what we see at the photonics level is that there are two big categories, and I'm oversimplifying, of course, but I would say that there are two big categories. So on the one side, we have comb generation using resonators. So the resonator that could be in silicon nitride, for example, here, or in fiber. So that's great work they are doing at the ULB, so the other university in Brussels. So Nicolas Engelbert and co-workers. So in both cases, it works very nicely. You can get very broadband combs, really broad bands with a reasonable performances. I'd say reasonable because typically the power balance is not so advantageous. You need a lot of power in and you don't get that much power out. But I mean, the bandwidth is really amazing. The difficulty here is mostly that the flexibility is low or even inexistent. Meaning that you have this cavity and it fixes the property of your comb, you cannot change it. So almost. So if you want to use a different free spectral range, so a different comb separation, then you need to change cavity completely and restart almost from scratch. The alternative is to work with, for example, electro-optics comb. So in this case, we take advantage of still the high flexibility of electronics, and we use an optical modulator to create an optical comb. So the flexibility is total. There's nothing really that prevents us from doing any kind of combs or any kind of comb properties. So, but the bandwidth is typically low. So one of the challenges, and it's what I explained roughly in this reference, the main challenge is how to expand this bandwidth, because the bandwidth is fairly limited to only the optical modulator bandwidth, or maybe sometimes 2 times the bandwidth, but it's fairly limited. So our proposal was to try to use multi-wavelength lasers, to kind of expand frequency combs. So when I'm saying expand, it's not broadening. You will directly see why, because we still have a problem with phase connection, phase correlation. But we can really expand the combs nicely. So what we try to do is just to inject a narrow optical EO comb. So we just you will see just after, but just with 5 lines, and see how we could trigger it, or how we could generate combs at the other wavelength, on the other available wavelength. So that's effectively the concept that we try to implement, and it worked quite nicely. So I will guide you through that. And we show, we were able to demonstrate that's also one of the perks, that if we have multi-wavelength laser with certain available wavelength, we could literally switch from any of these using our control technique. So we could really have some kind of tunable spectral multiplication very efficiently. Okay, so that's our experimental setup. There is nothing very fancy about it. So on the photonic integrated circuit, it's exactly what I just showed. So we just it's different artist view, but it's exactly the same thing. So we have the 2 dBrs, the SOA, and then the external cavity, so the feedback cavity. To go outside of the chip, we have a lens fiber, and then we go to the measurement equipment. On the generation side of the electro-optic comb, it's fairly standard as well. So we just have a tunable laser with Mach-Zehnder interferometer, Mach-Zehnder modulator, phase, polarization control, and EDFA. So that's the input that we are sending. And we are sending this, it's in blue to match this wavelength that we are sending in. So it's not shown here, and I don't think I have I don't have a plot. So when we have the laser without any optical injection, we only have emission at λ4. When we add this small narrow comb, well, we trigger emission at λ3, mostly because we have optical injection, so we are adding more gain to this λ3. So nothing so surprising there. Sorry. And what we see, we have also a certain broadening of the comb. What is interesting is that this λ3, we have this comb that is regenerated, that appears at λ3, and the initial emission, we also see something happening. So it's not so clear on this plot. I was hoping that it would be clearer, but okay. So we actually see also a comb. We will come down to that in a minute, but we also see a similar comb with matching properties at λ4. Then, if we take advantage of our electro-optic modulator, phase modulator that we have in our control loop, then we can efficiently switch between all these different subcomps. So we can get this kind, we can select lambda 1 here, we can select lambda 2 together with lambda 3, and so on. The only thing that we cannot do is suppress completely, everything except lambda 3, or suppress lambda 3. So lambda 3, the one that we inject, is always there. There is no real way to get rid of it. So this is quite visible in this plot here, where we show the optical power as a function of the EOPM voltage, and depending on the available wavelength. So that's with comb injection. Okay, we have very similar results if we just use injection without frequency comb. That is, if we don't modulate our injection. So this is really not. This is quite independent from the signal that we inject. So the big question when we are doing comb stuff is often the phase correlation, meaning that, okay, are the comb lines correlated or not? Are the comb lines nice, or is it not working so well? So if we isolate each of these comb lines, okay, we can see that with our spectrum analyzer, we can see that the comb lines are very well correlated. So each of these small combs, when isolated, so if I only isolate lambda 1 or I only isolate lambda 4, I can retrieve the same comb information, and all the comb lines are very nicely phase correlated. So at this level, the phase information, so the comb properties are perfectly preserved during this spectral multiplication. So through the coupling of the multi-wavelength laser, we achieve a complete transfer of this of the comb to other wavelength. What is, however, not transferred, and I don't have a picture here to show it, though. We are actually finishing the review of this paper, and so it was asked by one of the reviewer, which I think rightfully asked by one of the reviewer. We don't have a picture showing that the bit node between this comb and the next one is actually good. We don't maintain phase locking between the different combs. So the different wavelengths are not phase locked to each other. So it's only the comb lines. So if you really isolate each comb, there you have phase locking. If you try to look at different combs, subcombs at the same time, then you don't have locking. We found a way to actually, actually make them locked. I'm not going too much into the details, but what happened is that we tried to achieve this phase locking of different wavelengths, and one relatively simple way that we could think of is that, well, we could add an extra tone in your injected signal. So as you see here, this injected signal is added at F tone, which is matching the separation between lambda 3 and lambda 2. So that's how the laser is emitting without injection. In this case, we're adding quite a lot of power in both lambda 3 and lambda 2, so lambda 1 will be suppressed, as you will see. So in this case, as I said, well, lambda 1 gets killed, literally. But we now have these two nice subcombs. So the one that is initially injected with the comb line, and the one that is just seeing this extra F tone plus the internal coupling. And so what happens is that now we have an excellent coupling between the two tones. So we achieve a very nice, in this case, broadening of the comb, because we maintain coupling. So, and when I'm saying that we have an excellent phase correlation, it's every time it works with it's below the resolution limit of our spectrum analyzer, so below 1 Hertz, which is matching our input signal with that we are sending in the modulator. What is even more interesting, in our opinion, was that we could tune this F tone, and we can improve this this locking a bit further. So by tuning the F tone, what we saw is that we could get to a state where we have a much lower line width of the different modes. So what happens in this case is that if we have f-tone in just the right range, so you see that's a typical line width that we observed when there is no phase locking, and then suddenly we were able to reach a much lower limit. So this was achieved with optically, so with a high resolution optical spectrum analyzer, not with the RF spectrum analyzer, which is why we have still a much bigger value here. But so this was clearly visible for the whole range. And in this case, what happens when we tune this f-tone just in the right range, we end up triggering the mode at lambda1. So instead of just having two combs, we successfully trigger the third one. And we see that when we use a bandpass filter, unfortunately, we don't have a photodiode and the RF spectrum analyzer that goes up to the 60 gigahertz. I mean, we are about 50 gigahertz for the whole signal here. We're limited to about 40 gigahertz. So, but selecting just these two combs, we see that we have a very nice, again, a very nice phase correlation between the subcombs. So by using this extra tone, we can lock the neighboring comb, which is, really expected. So that's not such a big news, but we can also somehow cascade it to the neighboring one. And then comes the question, would it be possible, and what are the requirements to really cascade it? Maybe instead of just with 3 modes, but cascade it with 4, 5, 6, 10 different modes. That's what we are really looking into right now. So briefly about the spectral multiplication in multi-wavelength lasers, I haven't put the link to our preprint, but okay, not a big deal. If you want to know more, don't hesitate to contact me. It's also on my Google Scholar page if you're looking into it. But we found this coupling in multi-wavelength laser that was allowing us to have copy paste literally of the input signal. What I didn't show here, but works also quite nicely, we can also copy paste data. So to use it as wavelength conversion. So we are looking into that in more details, but that seems to be doable with relatively good performances. So we reach about 1 gigabaud for now, but we're aiming for a bit more. The advantage is also that it's really easily scalable. We haven't seen, as you saw, we worked with different longitudinal modes, but we haven't seen any difference of performance if we go to 1.2 terahertz or if we go just to neighboring. Is a phase locking, and it's true that even though cascaded locking can help, we did not find at this stage practical solution to lock the neighboring comb, the comb that was far away. So if I go back a little bit, so we have here, you see here, we have 10 nanometer separation. We didn't find a satisfying way to lock this comb to the main one. So yeah, of course, we have a few ideas and maybe using a broadband comb to kind of synchronize all this, but this isn't really satisfying in all sense. We would like to do it in a compact and simple way, but okay, at this stage we haven't found what we're looking for. So, well, with this presentation, I hope that I at least triggered a bit your interest if you're not working with multi-wavelength lasers. I'm not advocating necessarily that everyone should switch to multi-wavelength lasers and forget completely about all the rest. No, not that extreme level, but I still quite convinced that we can do really much more with multi-wavelength laser than just our single wavelength laser, and try to go to this next step. So that's what I'm trying to do. We hope also that everything will become a bit easier when we have the implementation on generic platform that will become more reliable. It's getting there, but unfortunately progress is relatively slow for for a lot of very good reasons, though. Our colleagues are also working very hard, but yeah, it's slowly getting there. And finally, I think that's also one of our task in the coming years will be also to look into the mode coupling a bit more and try to see what can we control better by looking into it. So thank you very much for your attention. Thanks again for the invitation, and of course, if you have any question, don't hesitate. I think the microphone in the room is yeah.
Thank you very much for your nice presentation. So do you have any questions?
I have a question about wavelengths you produce. I know that optical communication wavelength is 1550, and for amplification of that wavelength, erbium doped fibers are used. I wonder what your active medium is. Is it erbium, or you used semiconductor optical amplifiers, and what is the active medium in that devices?
Sorry, I didn't mention it indeed. So the medium that we're using is the one that is used by our partner Smart Photonics. If I go back to it, so we're using with the platform of Smart Photonics, so they're using indium phosphide. It is a limiting factor that we are, because it's only working in the C-band. So as you mentioned, there are different alternatives that could also provide different wavelength that can also be very interesting for different applications. And it's true that at 1.55, it's mostly communication application. So if we want to break outside of communication, then it would be best to work at also different wavelength. Unfortunately, it's also a practical issue because we don't have this growing facilities in-house. So we are relying on an external partner. And the only reasonable option right now to have this photonic integration, to have all these actives on with lasers is indium phosphide. So they're competing, there are a few competing foundries that are working with indium phosphide right now. We chose Smart Photonics. It's working correctly with them. But yeah, if there would be other alternative platforms, we would definitely look into that. But I hope, I'm confident, but I hope it will come up in the future that there will be maybe gallium arsenide or something like this. But it hasn't reached the maturity level of indium phosphide yet. So because here we can really just we do the design and they do the manufacturing. It's relatively seamless. They have plenty of building blocks that are already available. So it's not like we have to know everything about the integration process. Because that's also something to consider. We are not doing the growth. We are not experts in photonic integration, let's say in the process itself. So we wouldn't be able to go to this level without a commercial partner. So that's why we are working mostly with indium phosphide. Thank you.
So any other questions? I guess there is not. Thank you very much again. This presentation was very inspiring.
Thank you for the invitation. That was very nice. Thank you.